Sleep and study. Don't forget to subscribe.
We started off this course by building a framework, talking about quantum mechanics in one dimension, where it is most simple and easiest to understand. Then we built up some formalism, talking about the mathematical structure of quantum mechanics. Now we're going to come back to where we started, except instead of talking about quantum mechanics in one dimension, we're going to talk about it in three dimensions. We live in three dimensions, so this is where the real-world examples start to enter quantum mechanics. First of all, how do we go from one dimension to three dimensions? If we're going to start off in one dimension, we ought to have counterparts for the concepts that we encountered in one dimension in three dimensions. In one dimension, we had a wave function, which was a function of position and time. In three dimensions, our wave function is going to be a function of position in three dimensions and time. Thankfully, it has not become a vector function. It is still only a scalar function, but it is now a function of 4 variables instead of only 1, or instead of only 2 here. We will see shortly that when we were talking about the time-independent Schrödinger equation, as derived from this full time-dependent wave function, we ended up with the solution to the time-independent Schrödinger equation were simply a function of position times e to the minus I energy time over h bar. We're going to find out something very similar happens in three-dimensional quantum mechanics. We'll get a function of position in 3 dimensions multiplied by the same exponential factor, e to the minus I energy time over h bar. The operators that will appear in the Schrödinger equation, for instance, in one dimension, we had, for instance, the position operator x hat and the momentum operator p hat. X hat and p hat in 3 dimensions are going to be vector operators. So instead of just having x hat, I'll have x hat, y hat, and z hat in a vector, or px hat, py hat, and pz hat in a vector. And the definitions here are more or less what you would expect. For instance, let's just say px hat is going to be minus I h bar derivative with respect to x. I have to start being more careful about the difference between total derivatives and partial derivatives now, since we're talking about functions with multiple variables. But hopefully the notation will become reasonably clear shortly. The full momentum vector operator here is going to be written then in terms of partial derivatives of x, y, and z, and we have some notation for that. Minus I h bar times this upside down triangle with a vector hat on top of it. This is the gradient operator from vector calculus, and this is going to be read as del or grad, or the gradient of, depending on whatever it's acting on. And this gradient operator here, as before, let me move this out of the way a little bit so my notation is less confusing. This full vector momentum operator is going to be minus I h bar and then partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z. So that's my momentum operator. The position operator behaves similarly. X hat here is going to be x coordinate multiplied by whatever you're acting on, the wave function. Similarly for y hat being y coordinate multiplied by, and z hat being z coordinate multiplied by. We also have counterparts for the sorts of expressions we got working with something like the normalization of the wave function, the inner product of the wave function with itself in one dimension, or the inner product of the wave function with itself in 3 dimensions, still going to be equal to 0. Whereas in one dimension, we had an integral from minus infinity to infinity dx of psi star psi for our inner product. In 3 dimensions, we have to be a little more in depth. We have to integrate from minus infinity to infinity dx, and from minus infinity to infinity dy, and from minus infinity to infinity dz. But the same sort of expression is going to be the integrand. We're just going to be working with psi star times psi. Whereas this had to be, good grief, Brant. The wave function is normalized, not equal to 0. The inner product of the wave function with itself is equal to 1. Our normalization integrals are equal to 1. And that's going to be true whether we're talking about 1 dimension or 3 dimensions. So for every 1-dimensional structure, we end up with a 3-dimensional counterpart. Our wave function is going to be a function of multiple variables, and consequently we're going to have to keep track of multiple coordinates and derivatives with respect to multiple variables. And when we do things like normalize or calculate expectation values, we're going to have to be integrating over multiple dimensions. The Schrödinger equation also converts to 3D more or less how you would expect. This is the Schrödinger equation as we wrote it at the beginning of the course, in all its generality. We have I h bar times a partial derivative with respect to time being equal to a Hamiltonian operator acting on our wave function. If I write this I h bar partial derivative of psi with respect to time and expand out what the Hamiltonian actually is, in terms of general operators, p hat squared over 2m acting on the wave function, plus the potential energy, which is now going to be v as a function of 3 dimensions, v of x, y, and z, multiplied by the wave function. This p hat squared operator now is a little bit more subtle. We have to think about what it means to square a vector operator when it acts on the wave function. But we're going to have 1 over 2m times p hat. And since these are vectors, we can calculate the square by taking the dot product. These aren't vectors, of course, they're vector operators. They're still going to be acting on the wave function. V psi, we don't really have to worry about, that's relatively simple. Now, this vector dot product here, what is that actually going to look like? Well, we're going to have p hat, which I told you before was minus I h bar times the gradient. Well, if I take both the minus I h bars and pull them out front, I'm going to get minus h bar squared, which looks familiar from what we had before when we were talking about the kinetic energy operator. P hat then is going to be derivative with respect to x, derivative with respect to y, derivative with respect to z in a vector. I'm going to be taking the dot product of that vector with, well, itself more or less to find out what this p hat is. But this p hat is directly acting on psi itself. So I'll write this as derivative with respect of psi with respect to x, comma, derivative of psi with respect to y, and derivative of psi with respect to z, all together in a vector. And since I'm taking the dot product here, I know the x component of this vector and the x component of this vector are going to be multiplied together. So I'm going to be acting with the x derivative on the x derivative, the y derivative on the y derivative, and the z derivative on the z derivative. And I'm going to be adding up all of the results, since that's what you do when you're taking a dot product. The result then is going to be minus h bar squared over 2m times second derivative of psi with respect to x plus second derivative of psi with respect to y plus second derivative of psi with respect to z, plus v times psi as before. There's notation for this as well, since it appears over and over again. This guy we write as del squared. This is called the Laplacian, and it's either read as del squared, or you may hear this symbol called nabla. Nabla squared, the Laplacian, del squared, it all refers to the same sort of thing. And this is nice because this is a geometric operator, and it makes no reference in this notation to the specific structure of the partial derivatives that are necessary to compute it. So this is something that is a geometrical object, really. It doesn't have anything to do with the coordinate systems that you're working with, which simplifies the notation a great deal, and also allows us to go from one coordinate system to another with much more ease. So our final Schrödinger equation in 3 dimensions now, the way we're going to be working with it in this chapter is I h bar times the partial derivative of psi with respect to time is equal to minus h bar squared over 2m times the Laplacian of psi plus v times psi. So that's our Schrödinger equation in 3 dimensions. This is the full time-dependent Schrödinger equation. Notice we have these partial derivatives with respect to time. So when I'm writing psi in this equation, it's psi of x, y, z, and time. Or if I was writing this in spherical coordinates, I would have r, theta, and phi and time altogether. One of the first things we did with the Schrödinger equation when we were talking about one-dimensional physical systems was to do separation of variables to try and separate the time dependence from the position dependence. We can do that in 3 dimensions as well, and it works more or less how you would expect. We have our overall time-dependent Schrödinger equation, and we're going to be looking for solutions to this of the form psi of x, y, z, t, for instance, being equal to some function of x, y, and z multiplied by some function of time. I ran out of space here, but that's what this is going to look like. We're going to look for separation of variables type solutions to this formula, or to this equation. And you can see, remembering the definitions of the Laplacian here, it only had derivatives with respect to position in it. The potential operator here, v, is a function of x, y, and z. There's again no derivatives with respect to time, no time dependence in this part of the equation. So the left-hand side of this equation is where all the time-dependent parts of the Schrödinger equation are going to become significant. So when I substitute psi as a product of r, a function of position, and t, a function only of time, into this equation, I'm going to get something rather straightforward. When I substitute r times t into a partial derivative with respect to time, the partial derivative with respect to time will act on t, but not on r. So my r can be written out front. I'll have r times I h bar d capital T d time. The right-hand side, this has derivatives with respect to space. For instance, this del squared here has second derivative with respect to x, y, and z in it, if I'm writing things in Cartesian coordinates. It doesn't have any partial derivative with respect to time in it, so I can pull my time part out front. So I'll end up with minus t times h bar squared over 2m del squared r, when I substitute r times t in for psi here. Likewise, I'll end up with v times r times t here. This is just simple. So I can actually factor out the time from the right-hand side of this equation. And to fully separate the position and time dependence, I'll take this whole equation and divide it by RT. And when I do that, I'll get I h bar over t times partial derivative of time of the t part with respect to time being equal to 1 over r times minus h bar squared over 2m del squared r plus v r. Pardon me. This is the same sort of structure as we got when we were doing separation of variables in one dimension, except now instead of separating one spatial dimension from one temporal dimension, I've separated 3 spatial dimensions from one temporal dimension. The separation works the same way. We have here on the left a function only of time, and on the right a function only of space. And if this equation, the Schrödinger equation, is going to hold at all positions and all times, I have to be able to plug whatever value of t and whatever value of x, y, and z I want into this equation and have it still hold. The only way for this to work is if these functions are rather boring. These functions have to be constants. These are the constants that we got when we did separation of variables before, and last time we called it E. Since you know where this is going, E is going to be the energy. So these left-hand side and right-hand side are both going to be constants. And it turns out the left-hand side being equal to energy is going to give us the exact same solution we got before. This equation, if I multiply through by t, divide through by I h bar, gives me partial derivative of t with respect to time is equal to minus I e capital T over h bar, which has the same sort of solution. It tells us that capital T as a function of time is going to be equal to, or at least proportional to, e to the I energy time over h bar. I forgot a minus sign. E to the minus IET over h bar. This is exactly the same as the equation that we got when we were working in one dimension, which is good because we peeled off 3 spatial dimensions. The temporal dimension is relatively unchanged in this process. We haven't gone to multidimensional time after all, thank goodness. The spatial part being equal to time, if I'm going to say this is equal to energy, the right-hand side here being equal to energy, I can multiply through by r. And this r equation now takes the place of our psi of x, our position part of the Schrödinger equation. The contents of this parentheses here are the Hamiltonian operator acting on the wave function. So what we end up with for our position part is, as before, h hat psi of x, y, and z, for instance. I'll just write it as psi of x since I don't want to commit to a coordinate system at this point. But psi of the spatial part of the wave function is the energy times the spatial part of the wave function. Note that the psi here is a function of x, y, and z only, whereas the psi here is a function of x, y, z, and t. I'm just going back to the notation we used when we were talking about one-dimensional functions, where psi could either represent the full time-dependent wave function or just the spatial part for the wave function. Griffiths uses lowercase psi for the spatial part and uppercase psi for the full time-domain part, but I have a hard time distinguishing between lower and uppercase psi's in my handwriting. So, at any rate, you get the idea. We end up with the same sort of time-independent Schrödinger equation in 3 dimensions as we did in 1 dimension, except now we have to work with 3 dimensions, so instead of just having a derivative with respect to x here, we have a derivatives with respect to x, y, and z. So this is really the same as we got before, only much more complicated. And the complications are going to make our life somewhat interesting over the next couple of days, which is really where a lot of the rich structure of quantum mechanics in the real world comes into play, because we'll start talking about things like angular momentum. And angular momentum turns out to be really crucial to the structure of atoms and molecules. That's about it for quantum mechanics in 3 dimensions as far as the overall structure of the Schrödinger equation goes. In order to check your understanding here, think about x hat and p hat and calculate the commutator. This, as before, is going to be x hat, py hat here, now minus py hat, x hat, where x hat is going to be the x coordinate operator, for instance, just x times whatever the operator is acting on, whereas py hat is going to be minus I h bar partial derivative with respect to y, having to do with the y component of the momentum. Work out the commutator of these, and then think about what this commutator implies in the context of the generalized uncertainty principle, which we studied in the last chapter. Can I measure both x position and y momentum as precisely as I want? Or what about x momentum and y momentum? You know from 1 dimensions that you can't measure x position and x momentum, but what about x position and y momentum? The separation of variables with the time-dependent Schrödinger equation in 3 dimensions to remove the time dependence worked exactly the same way in 3-dimensional space as it did in 1-dimensional space. What we got then was a time part that looked exactly the same as it did before, e to the minus I h bar, or I e t over h bar, as before, and a spatial time-independent Schrödinger equation. So let's take a look at the time-independent Schrödinger equation in 3 dimensions. Consideration of this will lead us to the topic of spherical harmonics, which is very important in many different branches of physics. So we'll spend some time visualizing what they look like. First of all, though, the time-independent Schrödinger equation we got looked something like this. The Hamiltonian operator times psi, acting on psi, is, as before, some kinetic energy operator, p squared over 2m, plus a potential energy operator, v times psi, gives us just a constant e, a separation constant from separation of variables, times psi. Back. Now, the really crucial part of this is this Laplacian, del squared. If I'm working in Cartesian coordinates, the Laplacian is relatively simple. Del squared I can write, and let me suppose that it's acting on a function here, to keep the notation simple, is going to be equal to the second derivative of psi with respect to x, plus the second derivative of psi with respect to y, plus the second derivative of psi with respect to z. The sum of the 3 second derivatives of psi with respect to the 3 Cartesian coordinates. This is our typical Cartesian coordinate system, x, y, and z. If we're working in Cartesian coordinates, great. This is potentially something that we can work with straight away. We'll see what that looks like in a moment. For now, though, I also want to give you an expression for the Laplacian in spherical coordinates. If we're working in spherical coordinates, our coordinate system looks something like this. Just to draw a Cartesian coordinate system for reference, we're working with some point that is a distance r from the origin. And in physics we call the polar angle, which goes from the z-axis to the vector that goes from the origin to r, we call that theta. And the azimuth, the angle around the z-axis here, let me draw that down here, we call that angle phi. So r, theta, and phi for distance, polar angle, and azimuthal angle is our coordinate system here. And in that coordinate system, our Laplacian in spherical coordinates is a good deal more complicated than our Laplacian in Cartesian coordinates. Del squared, acting on some function psi, is 1 over r squared times the partial derivative with respect to r of r squared times the partial derivative of psi with respect to r, plus 1 over r squared sine theta, partial derivative with respect to theta, of sine theta, partial derivative of psi with respect to theta, and yet another term plus 1 over r squared sine squared theta times the second partial derivative of psi with respect to phi. The reason we have such a complicated expression here is that spherical coordinates are not exactly independent. If I move in phi, for instance, the direction of my r unit vector changes. Consequently, derivatives of functions with respect to a coordinate aren't necessarily directly related to geometrical objects like the Laplacian. The Laplacian is something that is really independent of coordinate system, and since the Cartesian x, y, and z coordinates are all really independent of each other, the Laplacian has a simple expression. In spherical coordinates that's not true, so the expression we get is a good deal more complicated. Substituting in either of these expressions for the Laplacian in whatever coordinate system you want to work in will give you a concrete partial differential equation that you can think about solving. So first of all, let's consider what this equation would look like in Cartesian coordinates. Here's what you get when you substitute the Laplacian with neater handwriting into the time-independent Schrödinger equation in Cartesian coordinates. This is your sum of, and these should be second derivatives. This is your sum of second derivatives of your wave function with respect to x, y, and z. Your potential now must be expressed in Cartesian coordinates as well, x, y, and z. And, as before, that's the structure of our equation. What we want to do, if we're trying to solve this equation, since partial differential equations are difficult to work with, is to convert it into a system of ordinary differential equations. And we do that by separation of variables, essentially hypothesizing that psi of x, y, and z is going to be some function of x multiplied by some function of y multiplied by some function of z. If I make this substitution here, plug it in for psi, and find out what I get, well, you'll see what happens. We get something that we can actually separate out into three separate but coupled ordinary differential equations. So substituting in psi as a product of x, y, and z in, say, this term. This term is a second partial derivative with respect to x. That second partial derivative is only going to act on the part of psi that depends on x. It will ignore the parts that act on, or the parts that depend on y and z. So I'll end up with, first of all, my constant minus h bar squared over 2m out front. And then I'll end up with y, z, untouched, and then the second partial with respect to x of, sorry, it's not psi anymore, it's x. When I think about the second partial derivative with respect to y, I'll end up with much the same sort of thing, except it will be the x and z components that are untouched, and I'll be left with the second partial with respect to y of the y-dependent part of the wave function. Likewise for z, x and y untouched, second partial derivative with respect to z of the z-dependent part of the wave function. The rest of my expression here is relatively straightforward. V and then x, y, and z untouched equals e, x, y, and z untouched. I can ensure that these are actually separated if I simplify, and the easiest simplification step is to divide through by your wave function, divide through by x, y, and z altogether. That will cancel out the x, y, and z's here, and it will cancel out the y and z parts with the x and z parts with the y, and the x and y parts with the z. What you end up with then is minus h bar squared over 2m 1 over x, partial derivative with respect to x of the x part, plus 1 over y, partial derivative with respect to y of the y part, plus 1 over z, partial derivative with respect to z of the z part, plus v equals e. Now if, and there has to be some special circumstances here, if I can express this v in some simple way, if this v does not depend too much on x, y, and z, or if it depends on x, y, and z in a way such that I can put the x-dependent parts there and the y-dependent parts there and the z-dependent parts there, I can split this up. Looking at this then, I have something that is a function only of x, something that is a function only of y, and something that is a function only of z, plus potentially some constants coming along for the ride. If I have something that's only a function of x, and something that's only a function of y, and something that's only a function of z, all added up, and I want this equality to hold for all values of x, all values of y, and all values of z, the only way for this to work is if this is a constant, this is a constant, and this is a constant. These functions that I have must be essentially trivial functions in order for this equality to hold regardless of whatever I plug into the function as an argument. So for instance, in the case of this x term, I end up with a partial differential, or an ordinary differential equation now that looks something like this, minus h bar squared over 2m times the second derivative with respect to x of the x function divided by the x function is equal to some constant. I don't necessarily know what that constant is, I don't necessarily know what a good form for this constant would be, but I have a function only of x, and it's a differential equation involving that function. And the differentials are only with respect to x. So this is an ordinary differential equation. X is the only variable in this equation. It's the sort of thing that you could think about solving for x. You'll end up then with relationships involving these constants, and if you flip back in your notes, back to when we talked about how separation of variables worked in one dimension, you get a feel for what this sort of thing looks like. You can solve this equation, you find the x portion of the wave function, you can then go back and combine the different variables together in the same sort of way as we combined adding a time part back to our spatial solution to the time-independent Schrödinger equation. Here, you'll solve your equation for x, you'll solve your equation for y, you'll solve your equation for z, and once you find that, you can plug back in to find your overall spatial part, psi, as a function of x, y, and z. So that's all well and good. Cartesian coordinates works fairly straightforwardly. The separation is a relatively straightforward process. In spherical coordinates, that's not so true. We have a much more complicated expression for our Laplacian of the wave function psi. And, well, this is really the case that we often care most about, because this potential here is often going to be simply expressed in spherical coordinates. For instance, this could be a function only of radius. In the case of the hydrogen atom, which is what we're leading up to, this is decidedly a function only of radius. So let's see what sort of separation we can do in this case. First of all, let's think about pulling off a radial part. Psi of r, theta, and phi now, working in spherical coordinates, can hypothetically be written as some function of r multiplied by some function which I'll write as y of theta and phi. let's see what this separation works. Or let's see if this separation works, if we can peel off the r-dependent parts. Now when I plug this in, my partial derivatives with respect to r are only going to act on the r part. They're going to leave the y part untouched. And likewise, my partial derivatives with respect to theta and phi are going to leave the r part untouched. So what we're going to end up with then is, as before, minus h bar squared over 2m out front. Pardon me. Y over r squared, partial derivative with respect to r of r squared, partial derivative with respect to r of capital R, is our first term. Then the second two terms here are going to leave r untouched, so I'll end up with r over r squared sine theta, partial derivative with respect to theta of sine theta, pardon my notation here, sine theta, partial derivative of theta with respect, or partial derivative with respect to theta of y, my theta and phi parts. The third term, r, again being untouched, r squared sine squared theta, and then the second partial derivative with respect to phi of y, my theta part. My theta and phi parts, excuse me. And that plus v times r y, my wave function, is going to be equal to e times r y, my wave function. So that's what I get when I substitute this separation guess in here. As before, this isn't exactly separated. I have a theta and phi dependent term tagging along with my partial derivatives with respect to r. And here I also have an r squared tagging along with my theta and phi dependence, both for my theta derivative term and for my phi derivative term. So I've got to somehow get rid of that. And I can do that by, as before, dividing through. In this case, I'll be dividing through by the quantity minus h bar squared ry over 2m with also an r squared. So the division, to simplify things, is a little bit more complicated, but the overall result you get follows the same general structure, only more complicated. When I do that division, I end up with 1 over capital R, r squared, partial derivative with respect to r of r squared, partial derivative with respect to r of capital R, my first term, getting rid of the y, minus 2m r squared over h bar squared from my constants, plus where those constants get multiplied in. V, which is a function of r, minus e. That's what I get for the parts that have r in them after I've done this supposedly simplifying division. I also have terms, of course, from my theta and phi, which end up looking like 1 over y, and what am I left with? I'm left with a 1 over sine theta, partial derivative with respect to theta of sine theta times the partial derivative of theta with respect to theta of y, plus 1 over sine squared theta, second partial derivative with respect to phi of y. That, overall, these two terms added together, has to be equal to 0. And this is the same sort of structure as we had before. This now is a function only of r, and this is a function only of theta. We'll take a look at what you get from the function only of r later on. But for now, the same sort of analysis holds. This function only of r being essentially equal to this function only of theta means both of those functions must be trivial if this overall is going to hold for every r in theta. So we'll be left with, when we're done, this being equal to some constant, and this being equal to some constant as well. And in this case, the constants that we choose are a little strange, at least they will look strange for now. I'm going to say the constant here is going to be equal to minus l plus 1, where L is some constant. And the constant here is going to be L plus 1, essentially the opposite. So I have some constant and some opposite of that constant being added together to give me 0, which should make a certain amount of sense. The form of these constants always bothered me when I first encountered this subject. How do you know what to use for the form of your constants? Really, it doesn't matter. If you use a form of the constants that's slightly less convenient, you'll end up getting slightly less convenient expressions for the values of those constants and how those constants are related to each other. But it doesn't actually matter all that much. You're just saving yourself some trouble by choosing a convenient form for the constants. After you build up some intuition going through this separation of variables procedure multiple times, you will end up with a decent amount of intuition for what those constants should look like. But for now, let's focus on the angular equation. The angular equation has this complicated form, and it's going to be equal to this constant, L plus 1, with the minus sign out front. The way to simplify this equation, first of all, I want to get rid of these sine squared thetas in the denominator. So I'm going to multiply through everything by sine squared theta. When I do that, sine squared theta, I want to get rid of this y in the denominator as well. So I'm going to multiply through by sine squared theta y. That's what I'm doing. When I do that, I get sine theta, partial derivative with respect to theta of sine theta, partial derivative with respect to theta of y, plus second partial derivative with respect to phi of y. Canceled out basically everything. 1 over sine squared theta and 1 over y are both canceled out by this multiplication. That then is going to be equal to minus L plus 1 times sine squared theta y on the right-hand side. Now what I want to do with this is the same sort of thing that I did with the radial part. I want to do separation of variables yet again on this partial differential equation in an attempt to separate out the theta and phi dependence, keeping in mind this y is a function of theta and phi. So I will write y, hypothetically, y of theta and phi is going to be equal to capital theta, a function of theta, and capital phi, a function of phi. And I'll substitute this in for y and see what this gets me. If you go through that, the same sort of analysis, the same exact sort of procedure, substituting this in, my partial derivatives with respect to theta will leave my phi's untouched. My partial derivatives with respect to phi will leave my thetas untouched. And as before, I will want to divide through by theta phi to more effectively separate things out. When you do that, what you will end up with is this part is just going to be by itself. Since it has a theta dependence, I'm going to lump it together with this term. And what we'll end up with is sine theta over our theta function, partial derivative with respect to theta of sine theta, partial derivative with respect to theta of our theta function as our theta part. Having divided through by this, we've canceled out our phi dependence. That's where this 1 over the theta function came from. Our constants overall, well, they're not constants. Our term over here, which had a theta phi in it, which was then divided out, is going to instead appear on the left-hand side, being grouped together with our theta-dependent parts, plus L plus 1 times sine squared theta. Put brackets around that. Our phi part ends up looking relatively simple. 1 over capital phi, second phi derivative of our capital phi function. And this is all equal to 0. We've gotten rid of, that's all the terms we have to work with. So once again, we have a function only of theta here, and a function only of phi here. So as before, this has to be some constant, and this has to be some constant. And in this case, looking at this partial differential equation, you can probably guess that what we want to use for the constant here is something like m squared. In this case, I'm going to say this is equal to minus m squared, and this is equal to m squared. I've got a second partial derivative being divided by a constant. This part gives us an ordinary differential equation for capital phi as a function of phi. And just looking at that equation, very briefly, it looks like this. 1 over capital Phi, second partial derivative of phi with respect to phi. Sorry about all the phi's in the same equation, but this is conventional notation for this process, being equal to some constant, in this case minus m squared. If I rearrange this slightly, second partial derivative with respect to phi of our capital Phi function is equal to minus m squared times our capital Phi function. Second partial derivative of something gives you a constant minus a constant squared times your original function back. You should have, at this point, a pretty good guess what the solution to this looks like. It's going to be something that looks like e to the I m phi power. When I take the second derivative of this, I will bring down two I times m's, which will give me my minus m squared, times my original function. Exponentials like this are much easier to work with in this complex context, since I ended up with the minus sign here. For instance, if you had chosen a plus m squared for your separation constant here instead of a minus m squared constant, you would end up with real exponentials here. But you would find out later on that the only way that this could work is for m to be complex. For instance, if you recall back when we were talking about the Schrödinger equation in one dimension, one spatial Cartesian coordinate, we had to have the wave function psi be continuous. The continuity of phi in this context now, since phi is an azimuthal coordinate which goes around in a circle, we have to have phi at one end of the circle be equal to phi at the other end of the circle. Essentially, evaluating this function at 2 pi must give us the same thing as if we evaluated this function at 0, or else our wave function that would result from this separation of variables would not be continuous. So, if I plug this in, I'm going to end up with e to the I m 2 pi being equal to e to the I 0. E to the I 0, well, that's just 1. So, e to the I 2 pi times m is going to be equal to 1. You know what the behavior of e to the I m phi is. It's a complex number rotating around as phi increases. And if I'm going to have it get back to where it started in a complete revolution, m here has to be an integer. So if m is going to be an integer, for instance either 0 or plus or minus 1 or plus or minus 2, etc., I will end up with the solution, with a valid solution for my phi part here. Now this is not the full story, of course. This was just one piece of what we got from that overall angular equation. The more complicated piece comes from the theta equation. The theta equation is complicated, but excuse me for a moment, this is now the partial derivative of our capital theta with respect to theta, since we've already done our separation of variables. This is our equation for theta. We can simplify this a little bit, as before, multiplying through by the capital theta to get rid of this theta in the denominator, essentially. And what you end up with is sine theta, partial derivative with respect to theta, of sine theta, partial derivative with respect to theta of our theta function, plus L plus 1, sine squared theta, minus m squared, and I'll put this in square brackets and multiply it all by my theta function, is going to be equal to 0. This, well, this is complicated. At this point, we have to give recourse to the mathematicians, go ask them for their advice, and they'll tell you that this differential equation actually has a name, and the solutions actually have names as well. The solution here is that theta, as a function of angle theta, is given by any proportionality constant. As before, the Schrödinger equation is linear, so we can choose whatever proportionality constant we want, such that we can normalize our wave function, multiplied by something called an associated Legendre function. And it has a subscript L and a superscript M. This is not raised to a power, this is just a superscript. And in order to get this theta function, I have to evaluate my associated Legendre function at the cosine of the angle. These associated Legendre functions are a little bit like the Hermite polynomials we encountered when we were solving the quantum harmonic oscillator problem. The associated Legendre functions are given in terms of the Legendre polynomials. I'll write that out. P sub L superscript m of x, now just a generic argument, is more or less defined to be 1 minus x squared raised to the power given by the absolute value of m divided by 2 times the mth derivative of the P sub L of x, where P sub L of x now is a Legendre polynomial. So these P sub L superscript m's are the associated Legendre functions, and they're expressed in terms of the P sub L's, the Legendre polynomials. Mathematica knows about these, Sage knows about these, any computer algebra software worth its salt should know about Legendre polynomials. It may even know about associated Legendre functions. But P sub L of x, we have an expression for that as well. That's more or less defined to be 1 over 2 to the L times L factorial as an overall constant out front by convention to make normalization easier, times the Lth derivative with respect to x of the quantity x squared minus 1 raised to the Lth power. So if I want to know what the Lth Legendre polynomial is, I can expand this out by raising it to the Lth power, take the Lth derivative of what I got, multiply it by some constant, take the mth derivative of that if what I want in the end is the associated Legendre function of order L and m, etc. Looking at the structure of these functions, you're taking an mth derivative, which means m has to be an integer. To put this in context overall, in spherical coordinates we need theta to vary between 0 and pi. What that means is that x, being given by the cosine of theta, has to be between minus 1 and 1. So we're only looking at these Legendre polynomials over a specific domain. And finally, these Legendre polynomials are actual polynomials. This is going to be a polynomial of order 2L, so when I take the Lth derivative of it, I'm going to get a polynomial of order L. So the Lth Legendre polynomial is a polynomial of order L. If I differentiate an Lth order polynomial more than L times, I'm going to get 0. So this says, the structure of these functions, as I've written them here, says that if the absolute magnitude of m is greater than L, P sub L m is equal to 0, identically. What that means is that m can only be up to L, only be within L and 0, for instance. If L is 0, m has to be 0. If L is 1, m can be plus or minus 1 or 0. If L is equal to 2, m can be 0, let me write that out properly, m can be 0, plus or minus 1, plus or minus 2, etc. If L is n, m can be minus n plus 1, etc., up to n. That's what the patterns are looking like here. So we only have a restricted value set that's available for L and that's available for m. In particular, L is an integer and m is an integer that is between minus L and L. The Legendre polynomials are something that you can go and look up. And in this case, I've given you a few of them to look at and plotted a few of them. They have the same sort of nice properties that the Hermite polynomials have. There are orthogonality conditions, there are normalization conditions. But just to give you a feel for what they look like, the 0th order Legendre polynomial is just a constant. First order is a line. Second order is a parabola, the yellow curve here. Third order, of course, is a cubic, the green curve. Fourth order is a quartic, the blue curve. And fifth order is a quintic, the fifth order polynomial given by the purple curve here. So the Legendre polynomials are the sort of polynomials that you'll encounter when you do separation of variables with the Laplacian in spherical coordinates. For instance, suppose what I wanted to do is find the theta part of my time-independent Schrödinger equation solution with L equal to 2 and M equal to 1. So here I'm talking L is 2 and m is 1. P subscript 2 superscript 1 of x is given by 1 minus x squared raised to the power m over 2, 1/2 in this case. Then I take the mth derivative, i.e. the first derivative, of p sub l of x, the lth order Legendre polynomial. Now you could flip back to the most recent slide and look up what the definition for the lth order Legendre polynomial was, but let's actually calculate it out. In this case, I'm going to be taking the xth derivative of it, whatever it is, and if you go and look up at the definition of the lth order, in this case the second order Legendre polynomial, you find it's 1 over 2 squared times 2 factorial of the second derivative of the polynomial x squared minus 1 quantity squared. And I should make it clear the derivative acts on it after it's been squared, not before. So we can figure this out. This is the sort of thing we can just plug into and do the algebra. 1 minus x squared to the 1/2 power. And overall, I'm going to get a 1 over 2 squared, which is 4, times 2 factorial, which is 8. So I'm going to have a 1 over 8 out front. And then I'm going to have a first derivative of a second derivative, so I'm going to end up with a third derivative, d cubed dx cubed, of what I get when I square this out. And when I square this out, it's squaring a binomial. I'm going to get x to the 4th minus 2x squared plus 1. So, third derivative of x to the 4th. X to the 4th is what I start with, 4x cubed after one derivative, 4 times 3, x squared after two derivatives, and 4 times 3 times 2, x after three derivatives. If I take three derivatives of x squared, I end up with 0, and if I take three derivatives of a constant, I of course end up with 0 as well. 4 times 3 times 2, that's 24. So 24x is what I get here. So I'm left with 1/8, 1 minus x squared to the 1/2 times 24x. 24 divided by 8 is 3. And if I go back and think of what I want here is subscript 2 superscript 1 of cosine theta, I can evaluate this at cosine theta. P21 of cosine theta is going to be, where'd my equal sign go? Is going to be equal to 3 times 1 minus cosine squared theta to the 1/2 times cosine theta, just x. Now this 1 minus cosine squared theta, 1 minus cosine squared is sine squared. That's one of the Pythagorean identities for sine and cosine. And if I take the square root of sine squared, I just get sine. So what I'm going to get in the end here is 3 sine theta cosine theta. End of story. So this is our theta part. Now if I wanted to know what the full y of theta and phi would be, in this case, my phi part is given by e to the I m phi, where m now is 1, so it's just going to be e to the I phi. And my theta part here would be 3 sine theta cosine theta. So I have a theta part and my phi part, and I'm going to have some normalization constant out front, which I have not yet specified. And that will give me a particular y with L equal to 2 and M equal to 1. There are, of course, an infinite number of allowed solutions here, and these y solutions with various L's and various M's are called spherical harmonics. They're expressed in terms of e to the I m phi and the associated Legendre functions evaluated at cosine of theta, but really they're just y, L, M. Usually it's written y subscript L superscript M. It's a function of theta and phi. And if you properly normalize them, going through the normalization procedure as we would if we were trying to normalize a wave function, you end up with this sort of expression. This epsilon here, incidentally, is keeping track of signs for us. It's defined to be minus 1 to the m if m is greater than or equal to 0, and 1 if m is less than 0. So it's just keeping track of signs. There's nothing magical about this epsilon. These spherical harmonics have an orthogonality relationship. If you use the same L and the same M, and you plug all these things together, and you go through the rigmarole knowing about all the properties of associated Legendre functions, you can prove that they do obey an orthogonality condition, subject to this normalization, of course. The one point that I do want to highlight at this is the sine theta here. The reason there's a sine theta here is that we're working in spherical coordinates, and essentially this is a volume integral. When we were normalizing our wave function in one dimension, we simply had a probability density as a function of a single variable. Our probability density now, as expressed as, for instance, the complex conjugate of the wave function multiplied by the wave function itself, where here we're only looking at the angular part, is a density function in 3 dimensions. And if you want to know what the total probability of finding the particle anywhere in this context, you have to integrate over volume. And if you're integrating over volume in Cartesian coordinates, that's easy. The volume element in Cartesian coordinates is just dx, dy, dz. But the volume element in spherical coordinates is not just dr, d theta, d phi. It's dr, d theta, d phi times sine theta. And that's where this sine theta is coming from. We're working in spherical coordinates, and that rears its ugly head here as well. Finally, the L and the M, just to recap, L can be any integer, 0, 1, 2, etc. Can't be negative. M can be negative, and it can only vary from minus L up to L. So these spherical harmonics have a lot of nice properties, and they appear over and over again. Let's take a look at what they actually look like. This is the sort of structures you get. The central column here is for M equals 0. The first row here is for L equals 0. The second row is for L equals 1. So we have M equals minus 1, M equals 0, and M equals 1. The third row here is for L equals 2. So I have M equals minus 2, minus 1, 0, 1, and 2 for my allowed values of M. The color now is showing you 2 things. The intensity of the color shows you the magnitude of the complex spherical harmonic. The color itself tells you about the phase of the complex spherical harmonic. So I'm showing you both amplitude and phase of a complex number plotted in 2 dimensions, and since I'm plotting it in 2 dimensions in spherical coordinates, I'm plotting it over a sphere. For L equals 0 and M equals 0, it's simple. We have no phi dependence and no theta dependence. Everything is just constant. We have a uniform red color everywhere in the sphere. For L equals 1, we start seeing some colors other than red. For M equals 0, L equals 1, we have intense red at the poles, at the North Pole and at the South Pole, with a black band around the equator, showing you that you have 0 magnitude of the complex spherical harmonic for L sub 1, M equals 0, at theta equals 90 degrees around the equator. If I have M equals minus 1 or M equals plus 1, I actually have dark spots at the poles instead of intense color at the poles. And the difference between M equals minus 1 and M equals 1 is the order in which the colors go. Here I'm going from green to blue as I move to the right on the front face. Here I'm going from green to blue as I move to the left on the front face. If L equals 2, the structures are slightly more complicated. Here I have 2 black bands at various thetas for M equals 0, 1 black band at the equator, and black spots at the poles for M equals minus 1 and M equals plus 1. And if M equals minus 2, geez, I keep writing this wrong, M equals minus 2, you have an even more intense dark region near the poles, but nothing happening at the equator. Note also that the colors vary much more rapidly here for M equals 2 than for M equals 1. This is a slow change from green to purple as I go from one side of the ball to the other, and here I have that same change from green to purple and then back to green as I go around. So here I've got only 90 degrees, what took 180 degrees here. So the phase dependence you get here and the angular dependence is rather difficult to visualize, but hopefully the patterns are starting to become clear. the number of dark regions going down here, you have 0 dark regions with theta, here you have 1 dark region with theta, here you have 2 distinct dark regions with theta. You could predict how many angles at which there would be no amplitude to the complex spherical harmonic as a function of theta. As you go away from the m equals 0 column, you stop getting these dark bands with theta. Here I had 2, here I only have 1, here I don't have any, but you start seeing a dark spot at the pole, and you start getting angular dependence here. The colors start swirling around, and the further away you go, the more the colors swirl. This is only one way of representing the spherical harmonics. Just to show you another way that might look a little more familiar, this is the same sort of plot, only now showing red and green as opposite phases. Essentially, this is a different superposition of the phi part of the spherical harmonics. What you had for our complex spherical harmonics, the way our textbook, Griffiths, defines them, was just e to the im phi. There were never going to be any angles phi where there were zeros for the amplitude of that spherical harmonic. But if I superpose e to the plus im phi and e to the minus im phi, I can end up with zeros, the same sort of way that we ended up with zeros adding up sines and cosines. So this is now, instead of plotting everything on a sphere, this is showing you the amplitude in a radial sense in 3 dimensions. So whereas, for instance, this is, as before, L equals 0, L equals 1, L equals 2, L equals 3, and going vertically, we have M equals 0, 1, 2, 3, minus 1, minus 2, and minus 3. So going down that column, I had a dark band going around the equator here where they're showing you 0 radius going around the equator. Here I had 2 dark bands going around at specific angles, and they're showing you 2 specific sort of cones where there is 0 radius for this surface. The color that's being plotted here indicates the relative sign of the spherical harmonic on either side. If these look familiar from your chemistry class, they should. These spherical harmonics will play an important role when we go on to calculate what the wave functions of the electron in the hydrogen atom actually end up looking like. So, try to wrap your head around what these things actually look like in 3 dimensions. Spherical harmonics are important. Understanding what their geometry is and what their structures is also important. To check your understanding, go back and use the definitions and find what the L equals 1, M equals 1 associated Legendre function evaluated of cosine theta actually is. And then think about how many points in the x direction does this 7th order associated Legendre, or the 7th order Legendre polynomial equal 0? And then how many points along the x-axis does the 7th order Legendre polynomial converted into the 7-4 associated Legendre function equal 0? And finally, if m is equal to 3, what are the allowed values of L? Continuing our discussion of the time-independent Schrödinger equation in 3 dimensions in spherical coordinates, let's talk about the radial behavior. We saw that the angular behavior in theta and phi in spherical coordinates gave rise to spherical harmonics, but we left off the radial part. So let's see what the radial part looks like and what it gets us. In context, we're working through separation of variables in spherical coordinates for the time-independent Schrödinger equation in 3 dimensions. Our overall Schrödinger equation looks like this, and if we make the substitution that psi is equal to r, some unknown function of r, times y, some function of theta and phi, we get these 2 main pieces. The separation constant that works we call the energy, as before, and the angular part here, we can again apply separation of variables to this, y of theta and phi being expressed as some function capital theta of theta times some function capital phi of phi. And that gave rise to our YLM of theta and phi, our spherical harmonics. The radial part we put off, so let's see what that looks like. What does the radial equation get us? The equation that we're working with here has partial derivatives of r, it has r squareds, it has potentials, which here we're assuming are only functions of radius, since that's getting into the context of the hydrogen atom, which is our goal. And it has these L's, which we got from our separation of variables in the angular part. So we have some constants to work with, and this is the equation that we're going to be discussing. We can simplify this equation by rewriting it as in terms of some new function u given by capital R of r divided by, or multiplied by, r. Put another way, the function capital R of r is given by u divided by r. So u is a function of r, and if we make these substitutions in this original equation, the form of the equation simplifies slightly. For instance, I've got terms like the partial derivative of capital R with respect to r. If I write this in terms of u, it's the partial derivative with respect to r of u over r, and this doesn't look like it's getting very much more simple, but you'll see what happens in a moment. Taking the partial derivative of this, I now have two terms, and I can apply the product rule. One, applying the partial derivative to the u and leaving the 1 over r untouched, or alternatively, leaving the u untouched and applying the partial derivative to the r, in which case I get u over r squared with a minus sign. What I'm going to want to do next is figure out what this term looks like, for instance. And this is, well, it's r squared times d capital R dr. But I know what d capital R dr is now. So I'm going to erase that, and I'm going to substitute in this, which is 1 over r du dr minus u over r squared. You can see the r squareds are at least going to cancel out. So that's a plus. And then I still have this partial derivative with respect to r out front that I have to deal with. So if I substitute in there, I'm going to have, simplifying this a little bit, partial derivative with respect to r of r times u, r not times u, times partial derivative of u with respect to r minus u. And now I have a product here as well. If I let the partial derivative act on the r, leaving the du dr untouched, partial derivative of r with respect to r is just unity. So I get the partial derivative of u with respect to r. And if I let the partial derivative act on the du dr, leaving the r untouched, I get r, second derivative of u with respect to r squared. And then the second term here has a minus sign in front of it, but there's only a single term, so I get a minus partial derivative of u with respect to r. And wonder of wonders, my partial derivative of u's with respect to r's cancel out, and I have just a single term left. This is more or less the entire point of making this substitution. We can convert this relatively complicated combined expression with partial derivatives, multiplication, and then repeated partial derivatives into something much more simple. So our overall equation then, at this point, looks like r, second derivative of u, with respect to r, minus 2mr squared over h bar squared times v of r minus e, not close parentheses, times, capital R here is u over r, and that's all equal to l plus 1 u over r, again substituting in u over r for capital R. Looking at the structure of this equation, I have an r here, I have an r squared here, and a u over r, and a u over r. I can simplify this a little bit by multiplying through by 1 over r. I'll get rid of this r. I have then a 1 over r squared after I've multiplied through by r, which will cancel out my r squared. And I'll just have a 1 over r squared, sort of consolidating the r dependence a little bit. What you get after making some simplifications like that, and I'll rearrange the constants as well to get something that looks a little more familiar, we have minus h bar squared over 2m, multiplying through by minus 1 as well, second derivative of u with respect to r squared, plus our potential function minus h bar squared over 2m l plus 1 over r squared, that's our remaining dependence, multiplied by u equals e times u. This should start looking a little bit familiar. we have what looks like a kinetic energy operator, what looks like a potential energy operator, and what looks like the energy. We're sort of back to what we originally started with. This is our radial equation, and it is essentially identical to the one-dimensional Schrödinger equation, with this being our effective potential. We have our actual potential, which is the function of radius, plus this, what's called the centrifugal term. This potential here, if I plot this, the centrifugal term blows up as r goes to 0. Essentially, this makes it hard for the particle to exist near the origin if we have any non-zero value of L here. If L is 0, of course, the centrifugal term disappears, but if L is non-zero, there is effectively a potential that pushes the particle away from the origin. It's called a centrifugal term in analogy with the centrifugal force that you get when you're thinking about classical physics with particles moving in rotating frames of reference. For instance, swinging a ball around on the end of a string, you have to apply tension to that string to keep the ball going in a circle. This potential essentially takes care of the force, effective force, that wants to push the ball away from you as you're swinging it around on the end of a string. But otherwise, this is exactly the same as our one-dimensional time-independent Schrödinger equation. So let's see what happens. As an example, consider the infinite spherical well. Instead of considering the infinite square well, let's do this in spherical coordinates. Our radial equation now, the potential, V of r, and this is the potential, not the effective potential, has a relatively simple form. For particles less than a certain radius from the origin, the potential is 0, and for particles outside the well, the potential is infinity. The same sort of potential structure that we had when we were dealing with the particle in a box in one dimension. So, first of all, don't need orange. First of all, inside the box, our equation looks relatively simple. Minus h bar squared over 2m, second derivative of u with respect to r, plus h bar squared over 2m L plus 1 over r squared. That's our centrifugal term times u is equal to E u. So this is our radial equation for regions inside the box. We can simplify this a little bit if we make the same sort of substitutions that we made when we were working with the one variable particle in a box. Namely, let's define k squared to be equal to 2me over h bar squared, effectively multiplying through by this h bar squared over 2me squared. And what we get when we do that is the second derivative of u with respect to r squared is equal then, rearranging terms, to L plus 1 over r squared minus k squared, our constant which includes the energy, times u. That's the equation we have to work with. And we'll solve that in a minute. Outside, of course, well, v goes to infinity, so that's a problem. Essentially what that means is that our wave function has to be equal to 0. Putting things in terms of this u also has to be 0 outside. On the boundary, the question is what happens to the wave function as it approaches a, or as the radius approaches a. And the same thing happens in this case as has had to happen when we were talking about the particle in a box in one dimension. Namely, psi of r equals a has to equal 0, or u of a has to equal 0, put in terms of u. So our boundary conditions are relatively simple. The equation we have looks complicated and will end up having rather complicated solutions, but is at least straightforward to write down. And outside, of course, everything is easy. So, just as a basic case, what happens if L equals 0? L now is a separation constant we got from our spherical harmonics, so there is some freedom there. We may end up with solutions with L equals 0. What might those solutions look like? Well, if L is 0, our centrifugal term vanishes, and when our centrifugal term vanishes, we're just left with this for our radial equation. And if you look at equations like this, you should guess, well, I'm going to have something to do with exponentials because I have a minus sign here. Maybe I've got complex exponentials. But in this case, it turns out to actually be simpler to write u of r is a sine kr plus b cosine kr. That's reasonably straightforward. You can see plugging this into taking the second derivative, you're going to get out at minus k squared, and you're going to get your same solution back. Everything works out. So this is fine. This, though, is our solution for u. It's not our solution for r. Capital R, our actual radial part of our wave function, is going to be u divided by r, if you remember the definition of u. So I'm going to have a sine kr plus b cosine kr divided by r for the radial part of my equation. This is slightly problematic if you look at it. If I have some cosine part here, meaning this constant b, which up to now has been arbitrary, if I have some non-zero value for b, I end up with something that looks like the cosine of r divided by r. As r goes to 0, the cosine of r is going to go to a constant, it's going to go to 1, so I'll end up with a divergence, a 1 over r sort of divergence. That doesn't necessarily cause problems in general for wave functions in spherical coordinates, but in this case, since our potential is so simple, there's effectively nothing special about the position at the center of this sphere. If we displace very slightly from the center, the wave function wouldn't change. You could just as easily express the sort of functions that you would get. Thinking about things physically, if you were in the center of a very large spherical room, it would be difficult to determine whether you were actually at the center. So it's unlikely that the wave function diverges, that there's anything mathematically special about the wave function. So the fact that this blows up as r goes to 0 implies b is equal to 0. We don't want to have any divergence at the center, since nothing special happens to our potential at the center. If you want to think about your wave function, just conceptually here, as a function of r, it blows up. It would blow up as r goes to 0 if b was not equal to 0. Thinking about that in sort of two-dimensional space, for instance, if we're looking at a slice through the center, we would have a wave function that blew up at the center. Blowing up the center means you have sort of an infinitely sharp peak here, and that infinitely sharp peak would cause problems if you think back to our discussion of the momentum operator. We would have at least a discontinuity in the first derivative of the wave function as you pass through the point, and that would be associated with non-computable or infinite or whatever values of the momentum at the center. So since we want well-behaved solutions, we can't have any non-zero value for b. This is kind of a subtle point. Hopefully I didn't talk about it too much. At any rate, our wave function now, if L is going to be equal to 0, our wave function psi of r, theta, and phi is going to be some normalization constant times just sine of kr over r, and then we're going to multiply it by the spherical harmonic y, 0, 0 of theta and phi. But y, 0, 0 of theta and phi is relatively simple. It's just a constant. So actually, our wave function here is just going to be sine kr over r. Give me a moment to move things out of the way here. What this means is that this is the form of our wave function. We haven't yet specified anything about the value for k here, and as when we were discussing the particle in a box in one dimension, the boundary conditions are what fix a value for k, and what enforces quantization of the energies, of the allowed energies for the system. So if you think about the boundary conditions now, u of a equals 0. What that means, the only way that this part here, sine kr over r, can ever be 0 at r equals a is if sine of k times a is equal to 0. This is very similar to the analysis we did when we were talking about the particle in a box. This means Ka is going to be equal to some integer times pi. And here is an element of the integers. And if you plug back in for the definition of K, you end up with exactly the same expression we had before, that the energy of this is going to be n squared, pi squared, h bar squared, over 2ma squared. And I'll put this in a box, but it's really only true for L equals 0 here, and that's important. This is not a general expression for the allowed energies of the particle in the infinite spherical well, but it is an expression for L equals 0. We get the same sort of structure as before. So what do we get for L not equal 0? If L is not going to be equal to 0, the actual equation we have to solve is the same equation we were talking about before. And unfortunately, this equation is difficult to solve. Really, in order to solve this, you have to go and talk to an applied mathematician. And the applied mathematician will identify this for you as the spherical Bessel equation. This differential equation has a name, and the general solutions he would be happy to write down for you are given in terms of what are called spherical Bessel functions and spherical Neumann functions. J sub L of kr plus b times r times n sub L of kr, where J sub L are called spherical Bessel functions and n sub L are spherical Neumann functions. So those are special functions, much like sines and cosines. You can go and talk to applied mathematicians and you can learn all about the properties. There are orthogonality relationships, there are normalization conditions, there are integral formulas, there are derivative formulas, there are series expansions and asymptotic forms. There is a lot of mathematics that goes into this. But for our purposes, since it is useful to be able to calculate these things, the simplest way of writing them down is that J sub L, the spherical Bessel function, just treated as a function of some variable x, you can think of as defined as minus x to the L, 1 over x to the L, times the nth derivative with respect to x of sine of x over x. Likewise, the spherical Neumann function can be defined similarly, minus x raised to the L, 1 over x to the L, times the nth derivative with respect to x of the function cosine x over x. So the connection to sine and cosine is still reasonably clear. But yes, these are just special functions, and if you want to make some calculations with them, you can probably do it. There is a lot of mathematics that will assist you in those calculations. But there's no simple way of writing down a formula, just like there's no simple way of writing down a formula for, say, sine of x. This is our general function, or our general solution to the spherical Bessel equation, which is what we got by doing separation of variables. This cosine x over x in the Neumann equation, the spherical Neumann functions, also poses problems. N sub L of x blows up as x goes to 0. So what this means is that, again, in our general solution here, we have to have b is equal to 0 in order to impose some physical sensibility on our solution. We weren't allowed to have a cosine term if L equals 0. We aren't allowed to have a Neumann term if L is greater than or equal to 0, for that matter. So how do you actually do math with these things? Well, one way to do it is to go and look it up in Abramowitz and Stiegen. Abramowitz and Stiegen is one of the canonical reference guides that you see physicists cite all the time. Nowadays, people don't actually use books like this because we have computers, but this is, for instance, a table of common logarithms. No one really uses logs anymore, but there are more than 1,000 pages of useful formulas, integrals, derivatives, all of that nice mathematics. Or you can pull it up in your computer algebra software and make some plots. This is a plot of what the spherical Bessel functions actually look like. So this is related to our radial part of our solution. Sorry, this is our radial solutions. The red curve here, this is for L equals 0. We're looking at J sub L of x now. So this is L of 0, this is L equals 1, L equals 2, L equals 3, L equals 4, etc. is shown in blue. So as L increases, this thing sort of gets smooshed down near the center, which makes sense because as L increases, the centrifugal term becomes larger and larger, and the particle is therefore less and less likely to be found near the center, since doing so would require the particle to have more and more and more energy, essentially. One thing to notice is these are oscillatory functions. J sub L here for L equals 0 was our solution that we got when we gave L equals 0. So here, J sub 0 of x is just sine x over x, or is proportional to it. In fact, there will be a normalization constant here, of course, since we're dealing with wave functions in quantum mechanics. But sine x over x is going to have zeros at pi and 2 pi and 3 pi and 4 pi, etc. J sub 1 here also has somewhat periodic zeros. They're not as periodic, unfortunately. And that's what we need if we're going to figure out how our boundary conditions work. When we just had sine x over x, it was easy to tell where x was equal to 0, and we could tune the other associated constants, namely the energy of our wave function, the energy of our state, such that the constant multiplying here, x for instance equals to k times r, we could tune this k, we could tune the energy, such that we had a 0 at the outer wall of our spherical well. Knowing exactly where those zeros are, we know exactly what those energies should be. And unfortunately, the zeros for the higher order spherical Bessel functions are slightly harder to find. You really have to do them numerically. There's no closed form expression for instance, the 6th zero of J sub 4. So we make up some notation for that. I'm going to call beta n sub L is going to be the nth zero of J sub L. So for instance, this point here is going to be the first zero of J sub 1. And you can look up the values of these beta sub NLs in Abramovitz and Stegen. It's in chapter 10, according to Griffiths. So our boundary conditions look much the same as they did before. We just have to express them in terms of these unknown zeros. So again, U of A has to be 0, which implies that J sub L of Ka has to be equal to 0, which implies instead of Ka being equal to n pi, Ka has to be equal to beta sub nl. Depends on two things now, not just n, it depends also on L, where this beta sub nl is the nth zero of J sub L. If you make the same sort of expansion as before, you end up with the energy of our state in this context being h bar squared over 2ma squared times beta sub nl squared. So that tells you what the energy of a general solution to this spherical well potential. It tells you what the energy is if you know what the zeros of the appropriate spherical Bessel function will be. So our actual solution in the end depends on three things. It depends on n, the index of the zero that we're looking at. It depends on L, the separation constant in the separation of variables that gave us the spherical harmonics, the angular part, and depends on m, the constant that arose from the solution of the phi equation. And it's going to be a function of r, theta, and phi, and it's going to be given by, of course, a normalization constant out front, J sub L of beta nl r over a, multiplied by our spherical harmonic, ylm of theta and phi. So this is our fully general solution, and it depends on n, where n is an integer. L, I'll just say L is going to be 0, 1, 2. It's a positive integer. And m, which is anything between minus L up to L. So we have these three integers that we need to choose in order to uniquely identify a particular stationary state solution to the Schrödinger equation in all three dimensions. So that's how these things end up working. Solutions in higher dimensions like this, in 3 dimensions, often end up involving these special functions, in this case the spherical Bessel functions. Occasionally you can make arguments on the basis of continuity or on the basis of well-behavedness of your special functions that you can throw out certain subclasses of your solutions. But what you'll end up with is going to be indexed by some integers if we have a quantized solution, or some continuous variables, for instance the momentum of the state, if we had something that was not fully quantized. For instance, our free particle in 1 dimension. You can do a free particle in 3 dimensions just as easily. These are your stationary state solutions then, and as before, you can add your time dependence back in. You're going to get something like e to the minus iet over h bar, as before. And you end up with your full solution. The time evolution of an arbitrary initial condition can be expressed then as this in the same sort of way, using your Fourier's trick, using the orthogonality now of spherical Bessel functions and the orthogonality of spherical harmonics. You can express your initial conditions in terms of your stationary state solutions, add the time dependence on, and you have your answer. That's how these problems are typically solved. To check your understanding, here are a few basic questions just asking you to determine the structure of the solutions. What are the allowed values of the constants that we got here? And how many zeros are we actually working with in a particular case? How many values of r between 0 and a is this particular spherical Bessel function evaluated using these betas going to equal 0? Given the structure of the time-independent Schrödinger equation in 3 dimensions expressed in spherical coordinates, the hydrogen atom is the logical target. This is the simplest, actually physically reasonable, real sort of scenario that we can solve exactly with the Schrödinger equation. So let's take a look at that. The first piece of that, since we treated the Schrödinger equation with separation of variables, is to look at the radial wave functions. The overall context, our starting point, is the time-independent Schrödinger equation. We have this generic expression for the Laplacian, which is related to the momentum, in this case related to the kinetic energy. So this is true in any coordinate system, whether it's 1-dimensional, 2-dimensional, 3-dimensional, etc. If we express this Laplacian in spherical coordinates, and make our usual separation of variables guess, namely that psi of r, theta, and phi is going to be equal to some function of r times some function of theta and phi, we saw in the previous lecture that for potentials that are only a function of r, as we're considering in this case, the angular part here, y of theta and phi, actually gave us spherical harmonics, y Lm of theta and phi as our solution. The radial part was a little more complicated, since that's where the bulk of the interesting derivatives are in the Laplacian. And if we make the substitution u is equal to r times r, I should write it the other way around, r the coordinate times r the function of r, so this is now u as a function of r, we ended up with this as our radial equation as a result of separation of variables. You can see this in the previous lecture on the discussion of the time-independent Schrödinger equation expressed in 3 dimensions. In the case of the hydrogen atom, we have a very specific form for the potential here, namely that V of r is given by the usual equation from electrostatics, minus e squared over 4 pi epsilon naught 1 over r, where e is the electron charge, pi, of course, is pi. Epsilon naught is the permittivity of free space. Coulomb's constant, essentially, 1 over 4 pi epsilon naught. So this is our potential energy. In the case of a proton being orbited, and I really shouldn't draw this, especially in a quantum mechanics class, being orbited by an electron, the distance separating the proton from the electron is what determines the potential energy. And we have a minus sign here to imply that as the electron approaches the proton, it's actually losing potential energy, meaning it would be gaining kinetic energy if we were letting it fall into towards the nucleus. It's attracted to the nucleus, essentially. That explains the minus sign. So that's the potential function we have to work with. we can make this a little bit easier to work with if we make a change of variables. So the equation we have now, the radial part of the Schrödinger equation, expressed in terms of this redefinition u is equal to the actual radial function times r. We have a couple of constants, and we can rearrange the constants. For instance, we're going to do this by dividing through by the energy, dividing through by E, and we're going to make our usual definition of a constant k. K squared is minus 2me over h bar squared. The minus sign here refers to the fact that for bound states in this potential, which, looks like a potential well, we're going to have bound state energies that are negative. So if energy is negative, k squared is a positive number. There's no real problem with this. If we make these definitions and we make this simplification dividing through by E, we end up with 1 over k squared times the second partial derivative of u with respect to r squared. That's coming from this term. And that's all equal to, now rearranging some terms from the left-hand side to the right-hand side of the equation, 1 minus me squared over 2 pi epsilon naught h bar squared. And I'm rewriting this a little strangely. There's a k here, and then there's a kr, 1 over kr, plus l plus 1 over kr squared. And this is all acting on u, or multiplied by u in this case. So we just have our second derivative term. That's been moved to the left. The h bar squared over 2m has been taken care of. When we divide through by e, we've got 1 over 2me and h bar squared, so we have a 1 over k squared. The dividing through by energy means we've just got u on the right-hand side here, so that contributes this 1. Our array of constants here with an overall 1 over r sort of behavior is what we get from this term, which still has its original minus sign. And the h bar squared over 2me again gets us a k squared r squared in the denominator in this term, with the usual l plus 1 on top. So this pretty clearly suggests that we should make some change of variables. We have these krs, which always sort of appear next to each other. So let's make the change of variables. Rho is equal to kr. If we're going to re-express this as a function of rho, we need to define a new function, which I'll temporarily call w, as a function of rho. And by that I mean w of kr. I'm just going to say w of rho is u of r. So I'm re-expressing my function, except in terms of rho instead of r. We can then, using this definition of w, do things like calculate derivatives. For example, if what I want to know is the derivative of u with respect to r, since that's going to appear, for instance, in the second derivative here, the derivative of u with respect to r is equal to the derivative of w of rho now, with respect to r, which we can just evaluate by the chain rule. If I want to differentiate a function of rho with respect to r, first I differentiate with respect to rho, and then I multiply by the derivative of rho with respect to r. The derivative of rho with respect to r, of course, we know what that is. This is just k. So this is going to be k dw d rho. I shouldn't write p's, I should write rhos. Now, Griffiths takes some liberties with the notation here. He doesn't define a secondary function w. He leaves this in terms of u, implicitly treating u now as a function of rho instead of u as a function of r. I'm going to stick with his notation in spite of the fact that I find it a little confusing. I find it much easier to make changes of variables here if you change the function in addition to the variable. But overall, you can see what's going to happen here. I'm going to, instead of rewriting this in terms of w, I'm just going to rewrite it again in terms of u. But now, the second derivative of u, really w, with respect to rho is going to be given by expressions like this. And you can see for yourself, if you do the chain rule again here, you're going to end up with another factor of d rho dr. So we're going to end up with a k squared, appearing in front of our second derivative of u with respect to rho. So the second derivative of u with respect to r is k squared times the second derivative of u, i.e. w, with respect to rho. So the k squareds are actually going to cancel out. That's the purpose of doing this sort of change of variables. Our re-expression of u as a function of rho means we can sort of fold the k here in the denominator in with the dr, turning it into a d rho. When you do that, the final equation you get is second derivative of our new u function of rho with respect to rho is equal to 1 minus, and I'll define another constant, rho naught over rho, plus l plus 1 over rho squared, all multiplied by u. And this constant rho naught absorbs the complexity in this. Rho naught is defined to be m e squared, sorry, not m sub e, m times e, the electron charge, squared, divided by 2 pi epsilon naught h bar squared k. So we've defined some constants and we've made a relatively straightforward change of variables. And we end up with this as our equation. This is the equation that we're going to want to solve, and the approach we're going to take to solving it is going to be very similar to the approach that we took when we were working with the quantum harmonic oscillator in one dimension. We're going to, in the end, use a power series to solve this equation. But before we use a power series, it's good to think about what the solutions to this might look like for very large or very small values of rho in this case. If there are problems with those asymptotic forms, for instance, if the function blows up or if the function does something poorly behaved, it's going to be very difficult to represent it with a power series. So if we can somehow factor out or simplify, much along the way of separation of variables, those asymptotic forms, we may be able to simplify the expression here, or at least derive a simpler equation, or at least an equation which has simpler power series solutions. So let's take a look at what those asymptotic forms are. The first asymptotic form that you might think of is, let's see what happens when rho goes to infinity, i.e. very, very large rho. Well, if rho is very, very large, rho naught over rho is going to be very, very small, and l plus 1 over rho squared is going to be even smaller. So really the only relevant term we're going to have in our equation for u with respect to rho is this 1. So the equation we're working with is going to be second derivative of u with respect to rho is equal to u. Now, second derivative of a function gives you the function back. You know that sort of function. You know the solution to that. The general solution to that differential equation is u is a e to the minus rho plus b e to the rho. Whenever I take the derivative of an exponential like this, I essentially am leaving the function unchanged. This is just the original exponential. The first derivative of this term gives me a minus sign, but since I'm taking the second derivative, I'm going to get two minus signs, and I'll end up back where I started. So these are the sorts of solutions that you would expect for this ordinary differential equation. Now, since what we're looking at is rho going to infinity, this term behaves itself rather poorly. For very large rho, this term blows up. So we can't have that be part of our solution. If we're going to say b equals 0, then the solution that we're working with is just u is a e to the minus rho. That's one asymptotic form. For very large rho, we expect our overall solution to look like a decaying exponential. Keep that in the back of your mind. The other limit that we're going to work with is rho goes to 0. When rho goes to 0, this 1 is going to become utterly insignificant compared to 1 divided by 0, or 1 divided by 0 squared. If rho is a very small number, 1 over rho squared is going to be much, much larger than 1 over rho, is going to be much, much larger than 1. So this is the dominant term for very, very small rho. That means the equation that we're working with here is the second derivative of u with respect to rho is equal to l plus 1 divided by rho squared u. This should also look familiar to you. I take the second derivative of a function of rho, and I get the function back divided by rho squared. Now, if I told you the first derivative was the function divided by rho, and the second derivative was the function divided by rho squared, you should think along the lines of polynomials. For instance, suppose I took x to the n just as a function of x. If I differentiate this with respect to x, I'll get n, x to the n minus 1. If I differentiate with respect to n, again, I'll get n times n minus 1 times x to the n minus 2. And I can, of course, rewrite this as n minus 1, x to the nth, all divided by x squared. So this is the sort of behavior you would expect from a polynomial. It doesn't work for just any order of polynomial, though, because we have this constant here, and this constant has to somehow be analogous to the constants we get from the differentiation. If you go through and actually work out what the allowed values for n are under these circumstances, it turns out there are two of them. We end up with our general solution here being u is c times rho to the L plus 1, and the alternate solution is d rho to the minus L. Both of these will give me an L plus 1 and an L. This one will give me the L plus 1 first, and then the L when I get take the second derivative, and it will give me my original function back up to the reduction in the power of rho by 2, which you can take care of by dividing by rho squared. Whereas this term gives me a minus L, and then a minus L plus 1. So again, L plus 1, the minuses cancel out. And I've, again, reduced the power of rho by 2, which you can take care of by dividing by rho squared. So this is a legitimate solution. In general, however, what we're looking at is rho very, very small. And when rho becomes very, very small, rho to the minus L, where L is what we got when we were talking about separation of variables in the theta direction, we ended up with, L is going to be a positive integer. So we're going to end up with something that blows up here as well. What that means is that d is going to be equal to 0 in our solution, and our general solution then is just going to be c rho to the L plus 1. So those are the sorts of asymptotic forms that we expect to get. If we combine these together, what we're going to do is guess that my original function, u, expressed as a function of rho, I'm going to guess that I can simplify this by writing it as rho to the L plus 1 times e to the minus rho times some new function v of rho. And I hope to derive a differential equation for v of rho that is somehow more simple, or at least easier to represent with a power series than this original differential equation. So, did all of that help? Is this guess going to work? Well, the equation that we have to work with here has second derivatives of u with respect to rho. So we're going to need to take some derivatives. So du, d rho, let's start there, is going to be the derivative with respect to rho of our guess in terms of v. U of rho given by rho to the L plus 1 times e to the minus rho times v, our function of rho. Well, we have three terms in this equation, and we're going to have to use the product rule to evaluate this derivative. So first of all, I can let the derivative act on the rho to the L plus 1, and I'll get L plus 1 times rho to the L. The other two terms will be untouched, e to the minus rho, v. Next, I can let the derivative act on the e to the minus rho. That's just going to give me e to the minus rho back with a minus sign out front. So what I'll get for that term is rho to the L plus 1 untouched times e to the minus rho times v with a minus sign from the differentiation. Finally, I can let this derivative act on the v, which will leave the rho to the L plus 1 and the e to the minus rho untouched. And what it's going to give me for v is just, well, the first partial derivative of v with respect to rho. Since I don't know anything about v, I can't simplify that. But that's all right. That's what we're going to have for the first derivative. For the second derivative, you can, well, repeat the procedure. Sorry for the messy notation. This is L plus 1 here. The second derivative, you can imagine taking, again, the derivative with respect to rho of all of this. And I'll spare you the details. It's again going to involve the product rule, applied to this term, and then applied to this term, and then applied to this term. The second derivative of u with respect to rho, which is what we need for this equation, is going to be equal to something complicated, but I'm skipping out here. And finally, at the end, after doing a little bit of simplification and rearrangement, rho to the L, e to the minus rho, times this big long expression. Minus 2L minus 2 plus rho plus L plus 1 over rho times v we end up with something that doesn't have any derivatives applied to v, just from the derivatives applied to the other terms, the terms other than v, in these product rule type calculations. We also end up with terms that have first derivatives of v from only allowing one of the two partial derivatives to act on the v of rho. And those terms end up looking like 2 times the quantity L plus 1 minus rho times just the first derivative of v with respect to rho. And finally, we have terms that have a second partial derivative of v with respect to rho, and that's what you get if you make both partial derivatives in the chain rule or in the product rule act on the v, leaving the other two terms untouched. And in this context, since I factored out a rho to the L e to the minus rho, that term is rho, and that's it, there's no e's, sorry, rho times second derivative of v with respect to rho. So that's our expression for the second derivative. It becomes our new left-hand side. So let us rewrite all of this, and I'm going to use a little studio magic here, which may or may not work. I'm going to copy-paste that expression, and then I'm going to shrink it down so I have some space to work with. So this expression is just reappearing here. This is our new left-hand side. And it's going to be equal to, well, our right-hand side, same as before. Not much is going to change about this. 1 minus rho naught over rho plus L plus 1 over rho squared times u, which we've re-expressed in terms of rho to the L plus 1 e to the minus rho v. So let's see how we can manipulate this. This had better simplify quite a lot, or we've wasted our time. First of all, we have an e to the minus rho on the left-hand side and an e to the minus rho on the right-hand side. So we can cancel those out, just dividing through by e to the minus rho. Second of all, notice that we have an L plus 1 over rho times rho to the L. Whereas here we have an L plus 1 over rho squared times rho to the L plus 1. Here we have an L plus 1 minus 2 for the total powers of rho that are multiplied by this term. And here we have a rho to the L minus 1. These terms, this term and this term, are actually going to be the same. You can see that if you actually expand these things out, but I'm trying to save time and I'm trying to save space. So if you actually expand these out, this L plus 1 over rho and this L plus 1 over rho squared ends up canceling out because of the way the powers of the rho outside the expressions end up working out. So that's all well and good also. Finally, we have a 1 here multiplied by a rho to the L plus 1 and a rho here multiplied by rho to the L. Those are also going to cancel out. Since, if we actually expanded them out, they would have the same power. This would be rho to the L plus 1. This is going to be rho to the L plus 1. So we've lost this term as well. Finally, you'll notice that we have rho to the L plus 1, and we have an over rho here. You have a rho to the L, and that's all. So we're effectively, if I multiply in one of the rows from this rho to the L, I'll be able to cancel this 1 over rho out. Then I'll just have a rho to the L here and a rho to the L here. I've gotten rid of the other two terms in the square brackets here, so I can cancel out the rho to the L as well. What you're left with when you've done all of that for our overall ordinary differential equation for v is that rho times the second derivative of v with respect to rho, and I'm rearranging terms, moving things to the left-hand side so we have something that looks more like a typical ordinary differential equation, 2 L plus 1 minus rho, what we're left with from the right-hand side, from the left-hand side, multiplied by the first partial derivative of v with respect to rho. We weren't able to cancel anything out having to do with first partial derivatives of v, since of course there aren't any of them on the right-hand side, plus rho naught minus 2 L plus 1 times v. And that's all equal to 0. So this is what we get for our simplified ordinary differential equation now for v. Did this actually help? Well, you'll see actually that it did. The reason this is a useful thing to do is if you look at our original differential equation here, while it took a lot less time to write this than it does to write this much longer expression, we have a row and we have a row squared here, whereas these rows in the denominator don't appear in our final expression. That's because the rows in the denominator, for instance, those were relevant when we were considering the row goes to zero limit, and we factored out the dominant asymptotic behavior for the row goes to zero limit with this row to the L plus 1 guess. So the row to the L plus 1s ended up canceling out the 1 over rows in the denominator here. The 1 also ended up canceling out, and that was what gave us the e to the minus rho asymptotic term. So we don't have terms that look like these sorts of constants multiplied by u anymore, which is good. We now have something that we can work with in the context of power series. So let's go ahead and do a power series solution to this differential equation. The power series solution that we're going to use is the same as power series solution that we used in the context of the quantum harmonic oscillator. We're going to guess that v of rho can be expressed efficiently by a sum from j equals 0 to infinity of c sub j rho to the j. This is our guess. We can substitute that guess directly in for the v here, but we also need a first derivative and we also need a second derivative. So let's go ahead and calculate those derivatives. The partial derivative of v with respect to rho, using this power series representation now, is going to be given by the sum from j equals 0 to infinity of j, c sub j, rho to the j minus 1. If you're confused about how this happens, think about expanding this sum out. Actually write out the first few terms of this sum and take their derivatives, and you'll see that this actually works. I can also rewrite this, relabeling the index of the sum, essentially replacing j with j plus 1 everywhere here and replacing j with j minus 1 in the limits of the sum. What you end up with under those circumstances is the sum from j equals 0 to infinity contains the only relevant terms, j plus 1 times c sub j plus 1 times rho to the j. I'm rewriting the sum here because it's useful to have an expression for the first derivative of j that I can use that has a rho to the j in it. Since whenever you make a power series solution like this, at some point in this power series solution process, you're going to equate the coefficients of like powers of rho. In order for two power series to be equal, you have to have every coefficient in the power series be equal. So you're going to split up the overall sum into a series of equalities. That's what ended up giving us our recurrence relation when we were talking about the quantum harmonic oscillator, but I'm getting ahead of myself. This is our expression for the first derivative of our power series for v of rho differentiated with respect to rho. If I repeat this process again, taking the second derivative of v with respect to rho, I'm going to work with this power series now. Again, I'm going to end up with the sum from j equals 0 to infinity. Working with this, I've got a j plus 1 from before, then I'm going to bring down a j, and I'm going to still have my c j plus 1, and I'm going to end up with rho to the j minus 1 as the power here. I will not actually have to relabel the indices in this sum, since the only place the second derivative appears is multiplied by rho. So if I end up distributing this rho into the sum, I'll end up with a rho to the j. So let's actually see how that works out. My left-hand side of this power series expression now becomes rho times my second derivative of v with respect to rho, which is a sum, j goes from 0 to infinity, of j plus 1 times j times c to the j plus 1 times rho to the j minus 1. Just copying this expression for the second derivative in. The next term here has to be broken up into two pieces if I'm going to want to equate like powers of rho, because I have here rho to the 0 and here rho to the 1. So for the 2 times the quantity L plus 1 part of the first partial derivative of v term, I'm going to use my relabeled expression, the one with rho to the j in it straight. That will give me, after I've multiplied everything into the power series, a rho to the j power. So I've got a plus 2 L plus 1 And that's it. That's all that doesn't have a rho in it, multiplied by the expression for the first derivative of v with respect to rho. Sum from j equals 0 to infinity of j plus 1 c to the j, c sub j plus 1 times rho to the j. That's what we want. We still have to work with this minus 2 rho times the first derivative of v with respect to rho term. And for that, I've got minus 2 times rho, and for this I'm going to use the power series for the first derivative of v that has a rho to the j minus 1, since I'm going to be multiplying in a row, and I want in the end everything to be raised to the j power, or the rho's to be raised to the j power. So, substituting that expression in, sum from j equals 0 to infinity of j c sub j rho to the j minus 1 power, copying this in. Finally, I've got this term multiplied by my power series of j, and I don't have to do anything fancy for that. I've got rho naught minus 2 L plus 1, that's it, multiplied by my power series here. Sum from j equals 0 to infinity, c sub j rho to the j. Now, all of this is my left-hand side expressed in terms of power series, so this is all going to be equal to 0. So this is my power series representation of my differential equation. Since what I'm looking for is a power series solution, in order for this equality to hold, this polynomial, all the coefficients in this polynomial must be 0. So the coefficient of rho to the 0th power is going to be 0, coefficient of rho to the first power is going to be 0, etc. And since I can multiply this rho into this and get a rho to the j power here, likewise, I can multiply this rho in and get a rho to the j power here. The coefficients that appear in these sums are all already lined up. So if I take the j equals 0 term from each of these sums, I'll get a valid equation. If I take the j equals 1 term from all of these sums, I'll get a valid equation. This effort with relabeling indices was essentially to get all of these sums to line up. Pardon. So when I do that, when I equate coefficients, I no longer have any sums, and I just have j plus 1 times c to the j plus 1, no more rows either, plus 2l plus 1 times j plus 1, c to the j plus 1, minus 2 times j times c to the c sub j from this, plus this, rho naught minus 2l plus 1 times cj. And that all has to be equal to 0. This expression is actually something that we can work with reasonably easily. And I'm going to attempt to move it up to get myself a little more space to work with on the bottom here. Apologies for making the slide look cramped. But we have a c sub j plus 1 there and a c sub j plus 1 there. We have a c sub j there and a c sub j there. So I'm going to move the c sub j terms to the other side of the equation and factor out the c sub j. I'm going to factor out the c sub j from these two terms, leaving me with just these coefficients, the j plus 1 and the 2l plus 1, j plus 1. And I'm going to divide through by those coefficients. And what I do, or what I get when I do that, is that c sub j plus 1 is equal to j plus l plus 1 minus rho naught divided by j plus 1 times j plus 2l plus 2. You can factor out a j plus 1 from both of these terms, so that's where this factorization comes from, multiplied by c sub j. And this is something that we can really work with in the context of power series. This is a recurrence relation that if I tell you c sub j tells you c sub j plus 1. So if I tell you c sub 0, for instance, the coefficient that's multiplied by rho to the 0th power in my power series representation of v of rho, that will tell me c of 1. Knowing c of 1, I can find c of 2. Knowing c of 2, I find c of 3, etc. If you remember back when we were treating the quantum harmonic oscillator with power series, the quantum harmonic oscillator power series gave us a recurrence relation that told you c sub j plus 2 in terms of c sub j, not c sub j plus 1. And then we ended up with a power series composed of even powers of rho and a power series composed of odd powers of rho. And we had to separate those two. We don't actually have that in this circumstance, so this is actually a little bit nicer to work with. So this is our recurrence relation. Let's see what it does. The power series coefficients here, we're working with things that look like this. So it's useful to figure out what this is going to look like, because in theory, our power series might not terminate. And if it doesn't terminate, we may have problems with convergence. So let's examine what happens for very large powers. Large powers in this context mean large values of j. And if I make a large j approximation here, I have a j in the numerator and a j squared in the denominator, effectively. So what I'm going to end up with is something like c sub j plus 1 is approximately equal to, for very large j, 2 over j plus 1 times cj. What this actually ends up giving you is, for instance, let's consider what I would get for c sub j plus 2. c sub j plus 2 would be, this 2 is going to reappear and going to end up with 2 squared j plus 1, sorry for the mess, j plus 1, j plus 2, c sub j. So if this were the exact recurrence relationship that we had to work with, we would end up with something that's starting to look like the factorial here and starting to look like the nth power of 2 in the numerator. So we would end up with, for a large j approximation, something like c sub j is approximately equal to 2 to the j power over j factorial, all multiplied by our original c naught. So if this is the form of the coefficients of our power series, this should look familiar. This means that v of rho is approximately equal to, for large rho, c naught times the sum from j equals 0 to infinity. Assuming this is exact, we can start our sum at 0, 2 to the j over j factorial. It's not 2j, it's 2 raised to the jth power, times rho to the j. That's our representation of v of rho. And this power series should look familiar to you. This is c naught times e to the 2 rho. If you calculate the power series coefficients of e to the 2 rho, this is 2 rho to the jth power over j factorial. So x to the j over j factorial, that should speak exponential to you in the context of power series. This, however, should look familiar. What this means is that u of rho is equal to our c naught, rho to the l plus 1, e to the minus rho, e to the 2 rho. This was what we factored out before we made our power series approximation, our asymptotic forms, and now we've got e to the 2 rho back. So this is just going to give us e to the rho. This is in some sense expected, since we knew that we had an e to the rho sort of asymptotic behavior that we ruled out originally because it was not physically reasonable. So since we ruled that out as not physically reasonable, we have to also rule out this large j approximation as not physically reasonable. This is a valid solution to the differential equation, but it's not a valid physical anything, really, since it's blowing up for very large r. It's not going to be square integrable. This is not a valid solution. What this means, our assumption that there is a very, very large j that we can use to make these sorts of approximations, to make these plausibility arguments for blowing up. If there is no very large j in our sum, what that means is that our power series must terminate. So once again, the fact that this blows up means that the power series has to have some maximum power. It has to terminate. So what does it mean for this power series to terminate? It means much the same thing as when our power series for the quantum harmonic oscillator had to terminate. We had the same sort of problem. If the power series didn't terminate, things would blow up. So the fact that this power series terminates is going to give us the same sort of phenomenon as we saw in the quantum harmonic oscillator. It's going to give us quantization. What does termination look like for this power series? Well, it means that there's going to be some c, and I'll say j max plus 1. The power series coefficient 1 higher than the maximum power of j is going to be equal to 0. Once that's true, all the subsequent even higher powers still are also going to be 0, since c sub j max plus 2 is just given in terms of c sub j max plus 1. In order to have c sub j max plus 1 be equal to 0, I must have the right-hand side of this equation equal to 0. The only way the right-hand side of this equation can be equal to 0 if c sub j is not 0 is for the numerator of this equation to be 0. So that means I must have 2 times the quantity j max plus L plus 1 minus rho naught is equal to 0. Conventionally speaking, the quantity in brackets here is called n max, or just n. And what this equation then tells us is that rho naught is equal to 2n. Rho naught, however, was a constant. We defined it to be m naught e squared, sorry, I don't know where the naught came from, m e squared over 2 pi epsilon naught h bar squared k, where k was a constant we defined as usual to be k squared to be minus 2m e over h bar squared. If you combine all of these constants together, I now know rho naught is going to be 2n. So 2n is equal to this, and I can substitute in the definition of k to get my energy into this equation. I have an equation with nothing but physical constants, the energy, and an integer in it. And of course here has to be an integer since we're terminating our power series at, an integer power. What that means, after you solve all this equation, solve these equations for E, since E is really the interesting relevant physical parameter, it tells you that the energy is minus, and I'll write this in the traditional way, m over 2 h bar squared times E squared over 4 pi epsilon naught, quantity squared, 1 over n squared. This tells you the allowed energies of the hydrogen atom, essentially. So this is actually a really important formula since it tells you about the properties of something that actually exists in nature, unlike quantum harmonic oscillators and particles in one-dimensional boxes. These polynomials that we get that have these properties, namely it obeys this recurrence relation, solves the differential equation we started with, and terminates, are called associated Laguerre polynomials. And they have the same sort of special function type properties that we've been working with when we were working with sines and cosines and the Bessel functions and the associated the spherical Bessel functions and the spherical Neumann functions. Those special functions all had special properties. Associated Laguerre polynomials are no exception. They are defined in terms of the Laguerre polynomials as the associated Laguerre polynomial subscript q minus p superscript p is it's a function of x, and it's defined more or less by minus 1 to the p times the pth derivative with respect to x of the qth order Laguerre polynomial. So these L sub q's are called Laguerre polynomials. Not associated, just original Laguerre polynomials. And they essentially tell us what our radial wave function is going to look like. So these L sub q's are something that you can look up in the book. These L sub q minus p superscript p functions are again things that you can look up either in mathematical tables like Abramowitz and Stegen, or in the textbook, or online, or with any computer algebra software package worth its salt. But what these essentially tell us is the shape, and we can use them to calculate actual radial wave functions. Here are the first few, which are again the sort of thing that you can copy from the textbook. These have now been properly normalized, so there's a normalization coefficient out front. And I just want to point out a few patterns that you should observe in radial wave functions. So if you're trying to calculate radial wave functions and they don't obey these patterns, worry a little bit. First of all, notice that each of these has an a to the minus 3/2 power. The a here is defined to be, this is another one of those constants that shows up, 4 pi epsilon naught h bar squared over m e squared. This is a length, and it's called the Bohr radius, named of course for Niels Bohr. So this length tells you roughly the size of the radial wave function. It's appearing to the minus 3/2 power in all of these, more or less as part of the normalization constant. If a is smaller, you want your radial wave function to be larger, since you still need to cram all of that probability into a smaller space. You'll notice the next feature after this a to the minus 3/2 power, for instance here, or here, or here, is a polynomial in the variable r over a. So r over a is essentially the distance from the nucleus in units of the Bohr radius. After that polynomial, which you get, of course, from the associated Laguerre polynomials, you see an exponential. This is the exponential that we factored out originally, appearing once more. And it appears with 2 in it if I have 2 for that integer that was associated with my energy. It appears with 3 next to it if that integer that I chose for my energy, the n in the r sub nl here, is 3. What this tells you is that the larger the n, the larger the energy relative to the lowest energy state, and the larger the energy with respect to the lowest energy state, the slower the exponential decay is. Just to make sure the notation here is clear, this, for instance, is e to the minus r divided by 3a. So the r is divided by both the 3 and the a. So, normalization constant, a raised to the minus 3/2 power, an exponential in e to the minus r over a multiplied by some integer, where that integer is the same as the integer that you chose when you were determining the energy, and a polynomial in the variable r over a. So these are what your radial wave functions should look like in the mathematical context, and in the physical context, they look like this. These are difficult to plot because they both shoot up to large values, but I should emphasize that none of these are divergent. We removed all of the possible divergences in our factorization of our asymptotic solutions. The wave functions that diverge as r goes to 0 are not physically reasonable, since, well, infinite wave function is going to cause problems when you start calculating expected values of momentum and expected values of energy, if for no other reason than that. So if I continue this plot, this guy actually does reach the axis at a finite value. At about 3, it just doesn't show up very well on this plot. So if I look at R10, that's the red curve here, it just decreases exponentially. That was our term with, there was no meaningful associated Laguerre polynomial, there was only a normalization constant and an exponential. If I look at R20, that's the orange curve, now we have a slightly non-trivial polynomial. So we start off positive, this actually hits the axis here, start off positive, crosses the axis, goes negative, and then comes back. All of these things are exponentially approaching 0 as you go to very large values of the Bohr radius. And they have most of their support near the center. If I look at R30, that's the green curve, it hits the axis here. One of the patterns that you should notice is that if there's a 0 for the value of L, R10, R20, R30, the wave function is non-zero at the center. Whereas if there's a non-zero value for L, that's the second number here, for L equals 1 here, L equals 1 here, L equals 2 here, for the yellow, blue, and purple curves, the wave function goes to 0 at the center. And that should be unsurprising because the centrifugal term in our effective potential for our radial function, that was the term that looked like L times L plus 1 over R squared in our original radial equation after we'd done separation of variables and made our substitution. This, if L is non-zero, contributes a very large energy for radii that go to 0, which means the particle is unlikely to be found at that region with extraordinarily high energy. So the wave function essentially has to go to 0, since the potential, or the effective potential in this case, is going to 0, or is going to infinity, if we have non-zero values of L. So there's obviously a lot of complicated mathematics going on. The radial wave functions themselves are quite complicated, And we will spend quite a bit of time working with these functions and visualizing them and understanding what the spatial and angular structure of these hydrogen orbitals is. We'll also, of course, discuss what predictions we can make about the behavior of the hydrogen atom from, for instance, the formula that we got for the energy of the bound state for this particular radial wave function, for instance. Each of these radial wave functions has a different energy, and each radial wave function is going to have a different allowed set of spherical harmonics to actually give you what the hydrogen atom wave function looks like. And if you've ever seen pictures of hydrogen atom wave functions, you know they're rather complicated. At any rate, I think that's enough for now. To check your understanding, here are a couple of questions just breaking into the derivation process of the radial wave function and trying to explain in your own words why each of these features is true of the radial wave function. We now have a complete description of the hydrogen atom wave functions. Our starting point was the time-independent Schrödinger equation, expressed in 3 dimensions with a Laplacian of the wave function as part of the kinetic energy term. Applying our usual separation of variables to this function, meaning psi of r, theta, and phi, using spherical coordinates since our potential in the case of the hydrogen atom is a function only of radius, we're separating a radial equation from an angular equation. Our angular equation, the result of separation of variables, is this, and it's complicated, but the solutions we got after repeating the separation of variables, separating theta and phi, was the spherical harmonics, YLM, of theta and phi. This angular equation is something that you get many times in treatments of partial differential equations, like the Schrödinger equation, in 3 dimensions in spherical coordinates. These are the sorts of things that you get when you solve for the wave equation on the surface of a sphere, for instance. These spherical harmonics are essentially vibrations of a spherical membrane. For the radial equation, what we got after the separation of variables for capital R, that function, was this. And this equation was slightly more complicated. We didn't just get simple sorts of YLMs that we could write down. YLMs being given in terms of a set of orthogonal polynomials and complex exponentials in phi. We end up with the same sort of solution for our radial equation, though. The process is slightly more complicated. Our capital R of R function, we had to make some changes of variables, but what we got in the end was R sub nl as a function of R. As a change of variables, we ended up with a 1 over r, simplifying things to write things with this 1 over r factored out. And then factoring out asymptotic forms, and before we did a power series solution, we get r over an raised to the l plus 1 power times e to the minus r over na. Those were our asymptotic forms, and then we ended up with some polynomial of r over na. And these polynomials ended up being associated Laguerre polynomials after we did a power series solution here. So we have a complete mathematical description. This a, incidentally, is the Bohr radius. It's a length, about half an angstrom, if you plug in the actual values of the constants. So we have a great deal of math here. Let's see what this math actually looks like. Messy. The final normalized hydrogen atom wave function has 3 quantum numbers, n, l, and m. The energy associated with this is given only by the n quantum number. The L and the M come from our spherical harmonic portion, and we end up with some complicated normalization constants. Normalization constant out front, then we have our asymptotic forms for our radial function. The actual meat of the radial function is this associated Laguerre polynomial with various orders, and the angular part is given just by our spherical harmonics. So it's hard, looking at this, to visualize what this actually looks like. So let's consider some sample cases. First of all, n, l, and m is 1, 0, 0. This is the lowest energy, the ground state, and it looks rather boring. What visualizations like this actually show are surfaces enclosing regions where the particle is likely to be found. So really, this doesn't tell you with certainty what the wave function looks like, because the wave function is, of course, a complex valued function of all three dimensions. It's not simply the expression for a surface. Our radial wave function, for instance, if we plot it here, r of r, is going to end up just looking like a decaying exponential. If we're looking for where the particle is most likely to be found, we also need to consider the spherical harmonic component, but in the case of the spherical harmonics, L is 0 and M is 0, and the spherical harmonics are simply constant. So our wave function more or less looks like this function of radius only, which tells us that the particle is likely to be found near the origin. So if you have some threshold within which you're likely to, or you consider the particle likely to be found, say probabilities higher than this, you end up with radii less than some critical radius. And that's what this sphere is showing you. It's a sphere with some radius given by whatever threshold you happen to use. So if this was boring, let's find out what happens if we look at N200, or NLM is 200. Well, that one's kind of boring as well. It's not quite as boring, though. It's just difficult to see in this. If we sliced this in half, there would actually be a region where the particle is unlikely to be found inside this sphere. If we look at our radial function, again our spherical harmonics being trivial, the radial function is the only one that matters. It decreases, drops below 0, and then comes back. So if we have some threshold above which we're interested in, or we consider the particle likely to be found, say here or here, we actually have two regions where the probability of finding the threshold is, or finding the particle is above threshold, inside and outside. So if I slice this in half, if I draw a coordinate system, and I'm just going to show the bottom half of the sphere now, I would have some internal region where the particle is likely to be found, and some external region within which the particle is likely to be found. Sort of two concentric spherical regions where the particle is likely to be found. These are not disks, of course, these are spheres, so I really ought to shade these in accordingly, but that would just make the figure even harder to read. These cases where L and M are both equal to 0 have spherical symmetry, since the spherical harmonics, the part that gives you dependence on theta and phi, is trivial, it's constant. So for the case of of L and M both equal to 0, you just end up with concentric spherical sorts of shells where the particle is likely to be found. The number of regions where the particle is unlikely to be found, here, where the wave function crosses 0, is essentially given by n minus 1. In this case, we have one place where the particle is unlikely to be found, this region in between the two concentric spherical shells. If we go up to cases where L and M are not equal to 0, you get something like this. This is L equals 1 and M equals 0. Now we have two distinct regions here, and I'll draw this in cross-section. I'll make figures like this repeatedly in, say, the xz plane. And there's a region where the particle is unlikely to be found, on the xy plane, for instance. Which leaves us with two regions, one above the plane and one below the plane, where the particle is likely to be found. The fact that the colors are different here is telling you something about the relative phase of the wave function. The fact that these are sort of opposite colors, blue and yellow, are opposite in a circular sort of RGB, going from red to green to blue and back to red. Blue and yellow are on opposite sides of the circle, so these have opposite phases of the wave function. When the wave function is +1 here, it will be -1 here. When the wave function is +i here, it will be -i down here in this region. All of these are, of course, evolving in time, so if I made movies of these, the colors would be fluctuating, but they would always be opposite colors on opposite sides of the xy plane here. If you look at the case where M now is ±1, we get a slightly different shape. This may look a little unfamiliar if you're used to looking at pictures as drawn by chemists. Chemists don't like to deal with complex numbers, which is understandable. They're dealing with real things. Why would they need complex numbers? But in physics, we're dealing with wave functions which are expressed in terms of complex spherical harmonics. What that means, here our YLMs have something that looks like e to the I plus or minus 1 times phi. M is 1. So this is plus or minus Im phi. So I plus or minus 1 phi. So what we're looking at is phase of the wave function fluctuating as we move around in the phi direction. And the fact that the colors are different here indicates that the sign of the evolution of phi is different. For instance, here we go Roy G. Biv, red, orange, yellow, green, blue, violet, around clockwise, whereas here we go red, orange, green, blue, violet, around counterclockwise. So the direction of our evolution of phi here is opposite. It's hard to draw pictures in that cross-sectional plane sense that I drew earlier, if we're talking XZ plane for both of these. But they don't actually look all that different. Where is the particle not likely to be found? Along the z-axis. And for that, I'll draw a dotted line along the z-axis. If what you're used to looking at are the orbitals from chemistry, you're probably used to seeing pictures that look something like this. You have a blob over here, you have another blob over here. Or you have a blob over here and another blob over here, sort of along the x-axis or along the y-axis. You get these by combining superpositions of these two complex spherical harmonics. Essentially, what you do to construct the real spherical harmonics is to superpose the complex spherical harmonics. For instance, if I take this, which is e to the minus I phi, and this, which is e to the plus I phi, and I add them together, this is going to give me cosine phi plus I sine phi. This is going to give me cosine phi minus I sine phi, after I abuse the even and odd properties of cosine and sine. If I add these two together, for instance, I'll get cosine of phi plus I sine plus cosine minus I sine, and the I sine parts will cancel out, leaving me just with the cosine part. The cosine part, then, is going to be non-zero only along the x-axis, where phi is 0. If I combine them instead with the minus sign, I'll get the cosine parts to cancel out, and I'll end up with minus 2I sine phi. If you ignore the complex part by multiplying everything by I, for instance, you'll end up with just the sine of the angle, and you'll get something that's only non-zero along the y-axis. So you would get the same sort of two blobs that we saw when we looked at the case where m equals 0. So if you're seeing pictures with blobs off-axis like this, in the case where m is non-zero, you're looking at a chemist's interpretation of the spherical harmonics. We can keep going. I'm going to skip the case where NLM is 3, 0, 0, since you know what that's going to look like. It's going to have 3 concentric regions where this particle is likely to be found, and go straight to the case where L equals 1. This is m equals minus 1, m equals 0, and m equals 1. So once again, Roy G. Biv clockwise versus Roy G. Biv counterclockwise. For the case m equals 0, we don't have any complex exponential part, so we just have the plus or minus 1 sort of phase differences. We also don't have any azimuthal dependence, and our radial structure ends up having one radial node. So we're unlikely to find the particle at the origin. We're also unlikely to find the particle in this sort of spherical region here. And the angular regions where we're unlikely to find the particle depends on what spherical harmonic we're looking at. So in this case, we're unlikely to find the particle along the z-axis, and we're unlikely to find the particle at a particular radius. Same sort of picture for this one, except we're looking at azimuthal dependence in a different direction. Unlikely to be found on the z-axis, unlikely to be found at a particular radius. The picture for m equals 0 is that the particle is unlikely to be found on the xy plane and at a particular radius. So what I'm drawing down here is the structure of the nodes, the regions where the particle is unlikely to be found, since those are really the boundaries between the blobs in pictures like this. We can keep going higher still. This is if L equals 2 in the case of n equals 3. So the structures we get are slightly more complicated still. The case where m is as large as it can be here, this is m equals -2, m equals -1, m is 0, m is 1, and m is 2, always look the same. We have the particle unlikely to be found along the z-axis, and we have this sort of donut shape going around. If I draw my node pictures for this, my m is as big as it's going to get case is always going to look the same. It's unlikely to be found along the z-axis. If I draw my node pictures for this case, particle is unlikely to be found along the z-axis and unlikely to be found on the xy plane. So we have sort of two separate donut shapes. For the case m equals 0, the particle is unlikely to be found at two values of theta. So I'm going to draw two lines like this, and you'll have to keep in mind that these are representing cones rotated around in the xy plane. Essentially there's a cone here and a cone down here where the particle is unlikely to be found. I'm going to erase that since it wasn't terribly instructive, but you get the idea. There are two angular nodes, two places in theta space where the particle is unlikely to be found. The same pictures, of course, apply over here and over here as they did here. Particle, in this case, unlikely to be found on the xy plane and unlikely to be found along the z-axis. This particle being unlikely to be found on the xy plane really refers to a node in theta where the the spherical harmonic evaluated at theta equals pi over 2, rotating 90 degrees down from the z-axis, is 0. So that defines the xy plane. Similarly, of course, over here, particle is unlikely to be found at theta equals 0 or theta equals pi along the z-axis. So these are the sorts of structures that we get from spherical harmonics. If you make superpositions of these, the way the chemists like to, you need to keep in mind now that, notice we have 2 points along the m equals -2 and m equals +2 where the color is red. That's because we're looking here at something like e to the 2i phi, minus 2i phi in this case, and e to the 2i phi in this case. And when I superpose those, I'll end up with sine 2 theta or cosine of 2 theta. So I'll end up with pairs of blobs. If I draw that out in 3 dimensions, you'd end up with blob, 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 versus, in this case, the same sort of thing, but rotated 90 degrees. So sort of blobs on axis versus blobs off axis. It's very hard to tell given these tiny sketches. So I suggest you go and look at pictures from the chemist's perspective if you're curious. You probably have a chemistry textbook or can find pictures online quite easily. As before, in physics, we're not afraid of complex numbers, and we end up with these sort of circular shapes for the non-zero values of m in our spherical harmonics. From the chemistry perspective, I'm going to go back through these slides again. These spherical orbitals are called s orbitals. The L equals 1 orbitals here, where we have these blobs, or in our case, donuts, the blobs of the chemist's approach, are called p orbitals. And the case where L equals 2, we have the slightly more complicated structures. These are called d orbitals. The origin of those names comes from a really antique spectroscopic convention, where the spectral lines that are emitted by an element are named according to their structure. Sharp for s orbitals, principal for p orbitals, diffuse for d orbitals. We now know that that doesn't really have a lot of comparison or relevance to the actual structure of the orbitals, but the names have stuck. To check your understanding of what the hydrogen atom orbitals look like, here are a couple of things that you can try using the simulations at falstead.com. He has a hydrogen atom orbital visualization tool, and you can use it to make complex combinations. So there are some specific things that you need to do in order to answer these questions on those simulations, but I encourage you to play with this simulation and try and get a feel for what the orbitals look like, both from the chemist's perspective. Those are real real hydrogen atom orbitals, as opposed to the physicist's approach, which is the complex approach. So the specific sub-tool of this visualization that I'm suggesting you use here to answer these questions is complex combinations of orbitals with n equals 1 through 4. But you can look at the real orbitals as well and make combinations of the real orbitals as well. So that's about all I need you to understand about the appearance of hydrogen atom wave functions. These things are, of course, very important from the perspective of chemistry, but from the perspective of physics, it's really just these complex wave functions, which have a variety of quantum numbers and a variety of geometrical representations, a variety of geometrical structures. One of the key experiments that really got quantum mechanics started was spectroscopy. Bright line spectra of the elements. They couldn't really be explained in the context of what physics was known at the time, and we've finally gotten to the point now where we can use the quantum mechanics we've learned so far to explain these bright line spectra. At least some of them, perhaps. This is the spectrum of hydrogen, this is the spectrum of mercury, this is the spectrum of neon, and this is xenon. So, 4 gases, and we'll be able to explain successfully the most simple gas possible, hydrogen. Our discussion of the time-independent Schrödinger equation in 3D, separated in spherical coordinates as appropriate for the spherically symmetric potential of a charged particle orbiting a nucleus, gave us psi with 3 quantum numbers n, l, and m. I'm not going to reproduce the long, complicated expression for what these are, but you know the radial part is given by the associated Laguerre polynomials, and the angular part is given by the spherical harmonics. As we went through the solution of the time-independent Schrödinger equation, we introduced a variety of constants, and then requirements, in particular for periodicity in the phi solution, the convergence and well-behavedness of the angular solutions, and convergence and well-behavedness of the radial solutions, gave us quantization conditions that we used to construct these n, l, and m. The constants that we got, for instance, we defined a k squared that was given by 2me over h bar squared. That should look familiar. We found out that that constant had to be given by 1 over some a squared, some radius squared, times an n squared quantum number. This a value, the Bohr radius, is about half an angstrom. And the energies that we got, after unwinding all of those definitions that we made, look something like this. You have the energy of the nth energy level, the nth stationary state, the stationary state with n as the quantum number, is given by this constant times 1 over n squared. And that constant should look familiar. It's minus 13.6, or it's 13.6 electron volts, with a minus sign out front, signifying that these are bound states. Their energy is less than the energy of a free particle. So minus 13.6 electron volts over n squared, those are the energy levels of our stationary states. Our stationary states are not going to be stationary in reality because atoms bump into each other and atoms interact in random ways that we haven't described the physics of yet. But suffice it to say, perhaps, that these energies are not going to remain forever fixed. If I prepare an atom in, say, the n equals 3, a quantum state with n equals 3, it's not going to stay there forever. After a while, it will lose that energy, and when it does, it will emit a photon. The changes in energy that take place are energy carried off by the photon. So we would say, for instance, that if we had, say, n equals 3 goes to n equals 2, there's a change in energy here, and we would say the atom has emitted a photon. Correspondingly, if you have an atom in state n equals 2 and it's excited up to state n equals 3 by an electromagnetic field surrounding the atom, we would say this atom has absorbed a photon. This absorption and emission of photons, photon here is our shorthand term for a particle of light, or quanta of light, perhaps I should say quantum, of light, is really the crux of the matter here. All of our experiments that motivated quantum mechanics had somehow to do with the interaction of light and matter. With our treatment of the hydrogen atom, we now have descriptions of how we can calculate changes in energy on the matter side. We haven't really said anything about the photon side, and unfortunately for that we'll need relativistic quantum mechanics, which is a topic for another course. But at any rate, you know that light is going to be emitted and absorbed in quanta, and the energies of those quanta are going to be given by the changes in energy of the thing that we can calculate, the thing that happens on the atomic side. So these stationary states are not going to be all that stationary, and by plugging in numbers for initial and final energy levels, you can calculate out what the energy of the photon would be, what the change in energy of the atom would be. These transitions have names, and this is a very standard visualization of what those energies might look like. The y-axis here is an energy scale, and it has 0 at the top. Anything with energies higher than 0 is not a bound state. The thick horizontal lines here represent the energies of the nth energy level. Here's n equals 1, the lowest energy level, n equals 2, 3, 4, 5, 6, 7, etc., up to infinity, where the bound state isn't really bound anymore. It has essentially 0 energy. The transitions that are possible, for instance, if we're looking at the emission of light by a hydrogen atom, the atom is going to start in a higher energy level and drop down to a lower energy level. When it does so from an energy level 2, 3, 4, 5, 6, etc. up to infinity, all the way down to the ground state, n equals 1, we call that a Lyman line. The emission in the spectroscopic context has a particular pattern of energies that were first examined by, well, Lyman, and the lines are named after him. Transitions that start with 3, 4, 5, 6, etc. go up to infinity and drop down to the second energy level are called Balmer lines. Likewise, end state lines with n equals 3 are Paschen lines. There are also bracket lines. You don't hear very much about them. Even less common are the Pfund lines and the Humphrey lines, which you can imagine have a final state of energy 5 and energy 6. So these transitions are the sorts of things that you would expect from the energy structure that we calculated as a result of the time-independent Schrödinger equation with a 1 over r potential. The transition wavelengths can be calculated pretty simply. What we have here is an energy that we can calculate, and we know the energy of the photon is going to be given by Planck's constant times the speed of light, let's say Planck's constant times the frequency, or alternatively, Planck's constant times the speed of light divided by the wavelength. Note that this is Planck's constant, not h bar, the version of the reduced Planck's constant that we've been using so far. So when you actually go out to calculate these things, you can calculate wavelengths easily by using the expression we had for the energy change by the atom, using that as the energy of the photon. The symbol for photon is gamma, typically, and solving for the wavelength. Doing so, you end up with this sort of thing, and this is a logarithmic scale now, 100 nanometer wavelength, 1000 nanometer wavelength, 10,000 nanometer wavelengths, and these things fall in very specific patterns. The Lyman series, which ended with n equals 1 as the final state, so this is a 2-to-1 transition, the longest wavelength Lyman line. This would be a 3-to-1, 4-to-1, 5-to-1, etc., all the way up to infinity to 1. Likewise for the Balmer lines, 3-to-2, 4-to-2, 5-to-2, 6-to-2, 7-to-2, etc., up to infinity to 2. Same for the Paschen series, and the bracket series, and the Pfund series, and I forgot his name already, the Humphrey series. They all have these nice patterns, and they all overlap. And if what you're looking at is the visible spectrum of hydrogen, you're looking at the Balmer lines. There are probably other lines that are visible if you look at a, quote, hydrogen gas, unquote, source being excited by a gas discharge, high voltage, for instance. Those are likely due to impurities. And if you think about the hydrogen atom, well, that's going to behave differently than the hydrogen molecule. It's going to behave differently than the singly ionized hydrogen molecule. And spectra like this, even with just a single atom, and this is just as predicted for the hydrogen atom with just a single electron, you already have very complicated behavior. So if I flip back to my motivating slide here, this is just looking at the visible portion of the hydrogen spectrum, and you can now identify this as the n equals 3-to-2 transition. this as the 4 to 2 transition, 5 to 2, 6 to 2, and if you continue into the UV, 7 to 2, 8 to 2, 9 to 2, 10 to 2, etc., these are the Balmer lines of hydrogen. When you work with more complicated atoms with more electrons, you have far more complicated behavior, and this is unfortunately something that quantum mechanics still really cannot predict well. To check your understanding of all of this, I have some simple calculations for you to do. First of all, figure out how the formulas that we gave for hydrogen would change for helium. You still have just singly ionized helium. So a single electron, instead of orbiting a single proton, orbiting an electron or orbiting an alpha particle, something with 2 protons. So the charge on the nucleus is going to double, and that will change the energies. Then make some calculations of energies, figure out whether they would be visible or not, and as finally, calculate the longest wavelength. Identify the transition for the longest wavelength in the Lyman series. These are conceptual sorts of questions that you need to understand the structure of the energy levels of hydrogen in order to answer, and there are also some simple calculations to do. But the fact that you are capable of making these calculations is really a triumph of quantum mechanics. We started with something that is essentially just an equation, hypothesized, almost entirely without justification. And it actually seems to work. You can do separation of variables, you can go through a lot of complicated mathematics, which from the physics perspective is more or less just turning the crank, trying to solve this equation. And the structure that you get, subject to all of this interpretation we did as far as the probabilistic interpretation of quantum mechanics requiring normalization of the wave function, and the overall structure of all of this leads to calculations of real measurable physical quantities. And for instance, the answer that you'll calculate for this is something that you can look up. If you look up helium spectrum in Google, you will get lots and lots of matches, and some of them will include data tables with hundreds, if not thousands, of observed and identified helium lines. And the energies that you calculate, the energy that you calculate will be in that list. And that's really quite astonishing if you think about it. It speaks to the overall power of quantum mechanics.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.